Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. We are finished with most of the physics that we were going to talk about, or the fundamentals of the physics and of stars and astronomy, and now we're going to actually delve into utilizing that the physics that we were talking about in all the previous lectures to talk about stars, the galaxies, and the rest of the universe. It'll be a lot of fun. So let's begin at where most people do an astronomy class, the beginning with the sun. So the sun is the nearest star. So it's a really, really, really big object. It's the sun. It's huge. A million Earths could fit inside it. 110 Earths can fit across it. And it's a big, big, big thing. It comprises 99% of all the mass in the solar system. And so studying the sun as a star is the best thing we can do because, well, all the other stars are really far away. They're on the order of parsecs away or light years away. That's trillions upon trillions of miles. So we're going to look at the sun as a star and try to understand it. So what we're looking at here is an enormous prominence that comes off of the sun, and these enormous prominences are gas clouds that are lifted in the magnetic field of the sun, and as they travel out into space they can encounter the Earth and other planets, and they demonstrate that the sun is an extraordinarily active thing. So let's first now go through something I haven't done yet in this entire series. Let's give some questions about the nature of the sun and its properties. So you can go back through these, but I'll just read them really quick. How do you know that Alpha Centauri is a star that's nearly identical to the sun? There are clues inside of this lecture that are coming up. Okay, next thing, it's a math sort of problem. Assume that an airplane travels at 600 miles an hour. How long would it take you to go around the Earth, and how long would it take for you to go around the sun? So that's kind of a fun little thing. Try to figure that out. And if the sun is as big as the Earth, as you are as big as something, this is a compare and contrast. So big might mean volume, big might mean height or width or diameter. And so how big, so if you think of the sun as you are the sun, and then what would be something as small as the Earth compared to you if you were the sun. So now compare the mass of the sun to all the members of the solar system, individually and by groups and the entire thing. And the density. What is the density of the sun? Not numeric density. We could call it number density if we want, but that's going to be an odd one. But average mass density. Compare it to the air at sea level, the rocks that are typical for the Earth's crust, and typically the density of your body. And you're going to have to make some assumptions to figure out what the mass density of your body is. Yeah, make some assumptions and have some fun. Just figure out what they are. All right, and if you take a random sample of the sun and you see it as you find that it actually has the same chemical composition as a random sample on the Earth. But what are some of the differences? And how do we know that the sun's not a solid body? Compare the magnetic field of the sun to the magnetic field of the Earth and to a medical CAT scan device. That's interesting. Compare the surface temperature of the sun to boiling water, molten steel in a welder's arc. Those would be some fun things to Google and look up. And finally, how many gigawatts of power does the entire human race produce each year, and how does this compare to the sun's output every second? So you're going to have to Google that and look it up. It's a very interesting question. All right, so let's go on. The sun. The sun, we see at sunset. It is the thing that provides the light during the day. You feel its warmth at night, and it bathes the Earth as it orbits the sun, which means that the light from the sun doesn't just hit the Earth, it goes out in every direction. The purpose of the sun is not to illuminate the Earth. The sun has no purpose in the solar system. It's just the biggest thing in the solar system, and the Earth orbits it. So the sun's light and the sun's heat and the sun's rays and its influence goes out in all directions. We just happen to intersect it in a very, very, very tiny amount, and we get very pretty sunsets. All right, this is a picture from Astronomy Picture of the Day by Max Alexander. This was the sunset at Stonehenge. And what's interesting about Stonehenge is it's an astronomical calendar tool. And that dates back a very, very, very long time. And it's wonderful to go see that. So to see the sun setting over Stonehenge, it's wonderful. So we've been thinking about the sun and what its influences are as many, many cultures throughout all of history. All right, so Another thing then, if we go forward, Neil deGrasse Tyson at the Museum of Natural History noticed that twice a year the sun sets exactly down the streets of Manhattan and cuts across the avenues at 90-degree angles. So it sets directly between the buildings, and he coined the term Manhattanhenge. So if you go to amnh.org or just look up Neil deGrasse Tyson and Manhattanhenge, you'll find all sorts of stuff. It happens twice a year, and so you get to, this is a great time to be hit by cabs as they careen into the sunlight. So be very careful in the streets of New York and Manhattanhenge, because the cabs can't see anything. They really can't. Anyway, so there are some physicals, there's some symbols and some things that we need to look at that are relevant to the physics of the sun, and we're going to be talking about the bulk properties of the sun. So each one of these symbols has a little circle as a subscript, and the subscript is a circle with a dot in it. And the circle with the dot in it is the alchemical or astrological symbol of the sun, and we just appropriate it because it's easier than writing out sun or the sun or solar or something like that. So the first one is a rho. It's not a P, it's a Greek letter rho, and the Greek letter rho sub sun, and that's what I'm going to call that circle with a target in it. Rho sub sun is the average mass density, or the mass density of the sun. It might be the average, it might be the surface density, it might be the core density, but in this case we're going to call it the average density because it is the average mass of the sun, or the mass of the sun divided by the volume of the sun, and that'll be the mass density of the sun. The surface temperature of the sun, which is the capital T sub sun, will be the surface temperature that we associate with the photosphere of the sun. And that, or whatever, we might, or that's going to be our typical fiducial value, and we'll compare it to other things as well. M sub sun is the mass of the sun, and this will be useful all throughout the entire rest of all of astronomy. So we typically measure things in terms of solar masses. So the lower left capital M sub sun is incredibly important, and knowing that how much the mass of the sun is important. The radius of the sun also provides R sub sun, provides a fiducial value for a characteristic size of stars, and L sub sun is the luminosity of the sun, or the amount of energy it puts out in terms of light every second. So the luminosity of the sun in all wavelengths of light is what we call the L sub sun. So these are our bulk properties of the sun, and that's what we're going to be talking about. All right, what's the radius of the sun? Our sub-sun is 696,000 kilometers. And that's over 110 times the size of the Earth, which the Earth is about 6,371 kilometers. And so about 110 Earths fit across the sun, and if you multiply it out, about 1 million Earths could fit inside the sun. And you can see in this picture, there's a little tiny dot next to the sun that would be what the Earth would be if it were traveling that close. Luckily, the Earth never gets that close to the sun, so it would be burned up and quickly fall in. So the Earth is very, very, very tiny compared to the sun, and huge prominences, which are gas clouds, such as you see in this image, get lifted off the sun, and they're incredibly large, large structures that move very rapidly. So the radius of the sun is big, and it's a characteristic size scale for stars. So we're going to be talking about how big stars are, how small stars are, and the typical size is about 100 times the size of the Earth, which is a typical stellar size. All right, so when we look at the planets in comparison, we see that the planets are pretty small compared to the sun. Jupiter, even the king of the planets, which is 90% of all of the mass of all the planets, is in Jupiter, and it's only about 10 times smaller than the sun in terms of diameter. But Earth is about 100 times smaller in terms of diameter, and I like to include Pluto as, well, some people don't call it planet anymore, but I do, because I knew Clyde Tombaugh, the guy who discovered Pluto in 1929. He was one of my mentors at New Mexico State. He was a great guy. So I would like to move Pluto up to the planetary thing, and I even found these really cool children's wooden blocks the other day at a little knick-knack store that had Pluto as a planet. So go Pluto! Anyway, so there's the sizes of the planets with respect to the sun. This is not their distance, though. You can't do both at the same time. It's just not possible. You can do the sizes, but you can't do sizes and distances and do it relevantly on a computer. Well, at least on a computer screen. You got to get outside to do that. All right, what's the mass of the sun? Now we're going to start talking extraordinarily large numbers. So the mass of the sun, or m sub sun, is about 2 times 10 to the 30th kilograms. And so for those that are math disinclined, that x is a times. The 10 to the 30th is a 1 with 30 zeros after it. So it's a 2 times 10 to the 30th, or basically a number 2 with 30 zeros after it. That's enormous. Now the mass of this Earth is about 6 times 10 to the 24th kilograms. So if you wanted to put them on a balance, it would take about a third of a million Earths to balance the mass of the sun. So the sun is more massive than anything else in the entire solar system, including the Earth. All right, so the next thing is that we're looking at the average density. The average density is you take the mass of the sun and divide it by its volume. And the average mass of the sun works out to be, compared to its volume, is about 1,400 kilograms per cubic meter. That's how we read that. So rho sub sun, or density sub sun, is about 1.4 kilograms per cubic meter. Water is about 1,000 kilograms per cubic meter, and the Earth's average density is about 5,500 kilograms per cubic meter. So the Earth's average density is much more dense than the sun. So therefore, but the sun's much more massive, so there must be something a little bit weird maybe down in the core, something's happening. But the average density. It's not the same density at the core, and it's not the same density at the surface. The sun's density varies wildly, whereas the Earth's average density, by comparison, doesn't vary as much as the sun's does. All right. Next thing we talk about is the composition of the sun. What is the sun made out of? Well, it's about 70% of it by mass is hydrogen, which is just a proton. We can ignore for now the electrons, because the electrons are very, very tiny compared to the protons. And by mass, the helium nuclei make up about 28% of the sun, and about 2% are heavier elements, heavier than hydrogen and helium. So oxygen, nitrogen, carbon, neon, boron, uranium, iron, everything you can think of, everything else in the entire periodic table, that makes up only about 2% of the mass by mass of the sun. And that's why the average density is so low, because hydrogen is a single proton. The average density, most of what Earth is made out of silicon and oxygen, make up silicon dioxide, or things rocks. So rocky materials such as carbon, oxygen, nitrogen, iron, the heavier elements. The Earth doesn't have as much hydrogen or helium as the sun by comparison, so therefore the Earth has less. And that's the surface composition of the sun. The composition changes as you go deeper into the sun, but in general, if you were to average it all out by mass, the total mass at the surface is 70% hydrogen, 28% helium. All right, so that tells us something very interesting. And how do we know that the sun's composition is this? That's really critical. So, because has anybody been to the sun? No. Nobody's ever been to the sun. Nobody's ever scooped up anything from the sun. So how do we do it? We do it with spectroscopy, which we talked about before, and we will talk about soon. All right, so the average composition in terms of numbers of atoms, so we can then say, instead of just by mass, we can say the numbers of atoms, which is a different sort of concept of the density of it. But we see that by atoms, hydrogen makes up almost 90%, or roughly 90% of the number of atoms of the sun, which means it's 90%, 91% just protons zooming around, and about 9% helium nuclei just running around, which in a typical helium nucleus has 2 protons and 2 neutrons. And everything else is so much less by the total number of atoms. The entire sun is almost completely made up of just hydrogen. And hydrogen is not so massive, so therefore the mass is lower. And helium is more massive. You know, there's four objects in the core rather than just one, in the nucleus rather than one. So therefore, helium, being only 8% of the total, 9% of the total, you multiply that by 4, and you get really close to the total mass of that. But why isn't it 4 times 9, which would be 36? And that's because a significant fraction of the helium is in the form of tritium, which is, not tritium, which is light helium, sorry. Light helium, which is helium-3, which only has 1 neutron, not 2. So, but of all the rest, oxygen, carbon, nitrogen, silicon, magnesium, neon, sulfur, and those are the big ones. And notice what it's made out of. Oxygen and carbon are critical for life. Pretty much everything in there is critical for life except for neon. So it's interesting. These are really, really interesting things that the sun is made out of. All right. So okay, how does the sun rotate? There's another bulk thing. Well, we can measure the speed with which sunspots go around the sun, and we find that at the high latitudes, it's moving a lot slower than at the equator. So it actually rotates a lot faster at the equator than it does at the poles. So it's interesting. And inside, it rotates a different rate altogether, and that can be measured by what's called astereoseismology or helioseismology, looking at well, that's interesting. That last one of the 27 days inside is also strongly model dependent, meaning what is happening in the core of the sun and how do things change as they come out. But it also can be indirectly measured by looking at the vibrations or ringings or waves on the surface of the sun. Well, the real trick is that what we find is that simply because we see that happening, the sun is not a solid. There is no solid surface to the sun. As the sun rotates, it twists itself up. It's a big ball of gas. There's no place to land on. There's no hard surface. It is gas all the way down to the center. All right. Next, we look at the magnetic field of the sun. It's 10,000 times more powerful than the Earth's magnetic sun. And all of the features that you see on the surface of it, these bright spots, these hot spots, the prominences, flares, everything, all of the surface features are driven by the strong magnetic field of the sun. And that strong magnetic field is what it does is that if a charged particle, such as a proton without any nucleus, with an ionized proton, is on the magnetic field, it will follow the magnetic field line, so will electrons. And so what you see in that upper right-hand corner of the prominence is ionized gas that's being lifted off of the surface as the magnetic field changes. And the magnetic field changes a lot. It's it's flexible and fluid as a thing, and it originates, and it's the source of what we call space weather. And space weather is the thing that affects satellites around Earth and can cause power outages here on the ground. All right, what's the surface temperature of the sun? It's almost 6,000 Kelvin. T sub sun is about 5,800 Kelvin, and that's hotter than anything you find. Some things that you'll find that are that hot would be maybe special bulbs of light that you might see in a theater. So you go to a Broadway show, the tiny, 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 tiny bulbs might be about that hot. And but that's funny is that, well, is the sun burning? And if something's that hot, you'd expect it to be burning. But the answer is no, the sun's not burning, because what is burning? Burning is the rapid combining of oxygen with something made of carbon and to produce carbon dioxide. And it is the rapid change of chemical structure inside of something such that gases are released. But it's a fast oxygenating process. That's what burning is. And you only get burning when there's oxygen. Well, there's not a lot of oxygen on the surface of the sun, as we've learned. So why does the hydrogen glow? Why does the helium glow? It glows because it's really hot. And anything, doesn't matter what it is, it can be a solid, it can be a liquid, and it's a gas in this case. A gas can be so hot and so dense that it just simply glows. Now that's fascinating. So it is more like the glow of molten iron, but the sun's not molten. It's a gas. So molten's still like a solid that kind of moves. It's a fluidic solid. That's molten iron, or flowing iron, which is a liquid state of iron. But when we think about this, it's like the sun's not a liquid. It's a gas. It's not a solid. So it's in a state of gaseousness, and there's no crystalline structure to make up the sun of any kind. So it's just a hot, glowing gas that's not burning. All right. Then we say, well, if it's hot, what is the energy output? And the energy output is what we call luminosity. Luminosity of the sun, L sub sun, is a standard that we'll see all throughout an entire astronomy course. It's about 4 times 10 to the 26th watts, and that's the same as 10 billion 1 megaton nuclear weapons exploding every second. Now, how many 1 megaton nuclear weapons do we have on the surface of the Earth? At the height of the Cold War, it was on the order of a few thousand. So or 10,000 or so. Basically, there's more happening in the center of the sun than all the nuclear, maybe 500,000 times the total number of nuclear. Yeah, it's like, okay, 500,000 is about 500,000, and you take about roughly 10,000 or so nuclear bombs that might have been, or about 1 megaton or half megaton or kiloton nuclear weapons. Multiply out the total constructed number of nuclear weapons that have ever been constructed by the entire human race in its entire existence since we started building them in the 1940s and detonating them. You'd have to have 100,000 of those things, those events, those sets of nuclear bombs that have ever been constructed, the most terrifying weapons, to equal what the sun does every second. Wow. And that's more than we do in this wattage, the amount of wattage that the sun puts out every second, or joules per second. That's what 1 watt is. 4 times 10 to the 26 watts. That's more energy that's being put out per second than has been put out in the entire history of all the recorded since the Industrial Revolution. And that's what's happening every second. It's a lot of energy output. All right, so the energy output, that's fiducial value, L sub sun, which is 4 times 10 to the 26 watts. We'll see it again and again and again inside this astronomy course. And the solar constant is what we get from the sun. So the sun goes out, all the sunlight goes out in every direction, and at 1 astronomical unit away, or 93 million miles away, or 150 million kilometers, or million meters, 150 million, 150 billion meters, is 150 million kilometers is what we get. And that's equivalent to 13 normal light bulbs on a kitchen table. So take a standard desk, like you might get, and a standard work desk is about a square meter is about a meter squared. And so imagine you take 13 100-watt light bulbs and put them on your kitchen table, and then put your face right next to all those things. That's what the sun is putting onto the surface of every square meter on the surface of the Earth at the distance of 1 astronomical unit. That's what we get. That's what you get. That's what every place gets. That's 1 astronomical unit away, whether it's above the sun, below the sun, behind the sun, to the left of the sun, to the right of the sun. The Earth just intersects a tiny, tiny, tiny fraction of all of that output. And what we call that wattage per square meter at the surface of the Earth, we call that the solar constant. And the solar constant is the wattage that is received on the surface of the Earth per square meter. And it's an amazing amount of energy if you really think about it. So imagine you take, well, if it's 13 normal light bulbs per square table, imagine we hooked up light bulbs basically every 12 inches on the surface of the Earth, a 100-watt light bulb, and then turn them all on. That's what we would have to do in order to equal the sun's output that we receive on Earth every second. All right. Next, what kind of star is the sun? If we take the light from the sun, and pass it through a prism, and then compare it to other stars, what we find is that the sun is like what we call a G-type star, and specifically it is a G2, which means it's a little bit cooler than a G0, and it is a main sequence type star, or a G25 type star, and that's what we call that. So if we compare the sun's spectrum to other nearby stars, we find that Alpha Centauri, one of the nearest stars to us in the sky, is actually just like the sun, which is funny. It's about 3 light years, just a little bit, about 4 light years away, and it's one of the closest stars to us, and it has the same exact spectral signature as the sun, so that's kind of cool. So where does the light from the sun come from? And that is really the biggest question of all, and that's what we're going to really address in the coming lectures, is how the sun produces the light that it makes, and how long will it be able to do that? So that's a good question. And I think this picture is from a friend of mine, Stan Honda, who took this picture from, if you go to stanhonda.com, I think you'll see this picture on his website. This time, we're getting away from the basics, bulk properties of the sun, and we're going to talk about the sun's appearance. And what does it look like on its surface? So the sun, as you can see in this image, is in ultraviolet light or extreme ultraviolet light taken by the Solar Dynamics Observatory, which is an orbiting spacecraft, and with its arrays looking at 171 angstroms, which is approximately 10 times shorter than short visible wavelength light or extreme ultraviolet. This is called extreme ultraviolet view of the sun. And we can see all sorts of very interesting features on the surface. We see over on the left-hand side some loopy type structures we'll call prominences. We have the prominences seen top down, which are the darker structures. We see like wisps going away from it. We call that the solar wind or the corona. And we also see hotspots, which are also active regions, which might contain sunspots, and usually do. They contain sunspots or other active things. And down close to the what we might say the surfaces, it kind of looks hairy, and those things might be called spicules. But let's see those more close up. Okay, so first things first, when you're done with this video and looking at it, you should be able to answer these questions and others. So do take a look at them and take a look and see if you can figure out them, and pause this thing and go back and look. All right, so this image of the sun was taken by Dr. Vishnu Reddy from University of Arizona. He was in Glendale, Wyoming with myself. I saw the total solar eclipse of 2017, and it was wonderful to go see. When the solar eclipse occurs, you get some amazing views of the sun. So why do we study the sun? There are numerous things, and we'll discuss these four in brief right now. We study the sun because there's a connection to our climate. Since it's the primary source of light and heat on Earth, everything that the sun does can influence how warm or hot the Earth is, and so it is the fundamental driver of all climate on Earth. So when we know about what's happening on Earth, we can know about the history of the climate on Earth. If we know about the history of climate on Earth, we can understand, maybe potentially help us understand what might happen in the future on Earth, and as possibly if we can understand short-term variations and their effect on the Earth's climate, that would be good too. All right, so first and foremost, we study the sun for that. Also, very practically, we study space weather. The sun, as you saw in that first image, emits what we call the solar wind, or particles are continually streaming off of it. Enormous amounts are continuously streaming off the sun and flowing out past into the interplanetary space. So this flow goes extraordinarily fast. It transmits it carries the sun's magnetic, or carries the print of the sun's magnetic field with it. And as it does so, it pumps the energy of the sun's magnetic field into the Earth's magnetic field, and that can influence satellite communications, as well as satellites themselves. If it's an extraordinarily enough violent solar wind flow for whatever reason, then the Earth's then planes might need to be grounded, or if it's a very violent geomagnetic storm, there might be power outages on Earth. So understanding the nature of space weather, or what the sun is doing to the space between and in the environment between the planets, is incredibly important. Because without understanding it, we can have big problems, as we'll see later. Third, the sun is a star. And while the first two are really important in terms of very practical aspects for life on Earth, the third one is the nature of astronomy, of course, because the sun's a star, and since it's the nearest star, it allows us to understand details about other stars. So it's the metric by which we judge all other stars. And understanding how stars work, it starts with the sun. And we should be able to expect that if we go, or we're able to imagine ourselves next to another star, we start first with images and thinking patterns of the sun, and then try to imagine what it might be like different over there. And in fact, the sun as a star fundamentally tells us the nature of what stars are, and stars are the building blocks for galaxies. And then if we think about then galaxies are separate things we'll talk about later. So the physics of stars are very important, and how the sun behaves as a star is important. Finally, there are some very interesting questions in physics that come out of studying the sun, and you can, instead of building multi-billion-dollar large hadron colliders and so forth, you can say, well, I've got this idea about how the nature of physics works, and what is the nature of physics, and how do particles interact on a nuclear level. You can say, well, the sun has to be doing nuclear fusion, and we'll see why in future lectures, that the sun produces the energy that we see by nuclear fusion. And as such, that nuclear fusion then gives us a test, a way to test our understanding of nuclear physics. So this is a really interesting way of talking about it. So in short, we have some important reasons to study the sun. So some other outstanding questions about the sun in terms of the future, which we might not actually get to, but we might in future times, is that how does the corona of the sun get heated? Nobody really knows. The complexity of which a solar flare arises, that's still an open question. It's mostly open, but the basics are understood. But how difficult it is to actually understand where a solar flare comes from, and we'll see what those are shortly. And sunspots come and go on the surface of the sun. That's incredibly important understanding because that links to climatic change apparently as well. And missing neutrinos is a particle physics question. So those are some principal questions. Some of these are answered better than others, but these are some incredibly important questions about the sun. All right, now everything that we're going to see about surface features on the sun is related to the magnetic field of the sun. The magnetic field of the sun is many thousands of times stronger than the Earth's magnetic field. And all of the things that we see on the surface of the sun, all of the surface properties are because the sun's magnetic field is not uniform and varies wildly and varies rapidly and can vary and changes with time. Unlike the Earth's magnetic field, which appears to be stagnant at the Earth's surface, it too is changing, but not with the dynamics of the sun. So the sun's magnetic field does everything. And one of the major satellites that's observing the sun today is called Solar Dynamics Observatory, and that's a NASA-based mission. And it has a series of telescopes and an ultraviolet exploration, and it also is able to detect motions on the surface of the sun, which allows it to image the magnetic field on the surface of the sun, and it takes images of the sun in various wavelengths, 10 wavelengths every 10 seconds, or one of those wavelengths every second. So the Solar Dynamics Observatory is designed to see very fast changes in order to understand what the entire disk of the sun is doing. Previous missions, such as Stereo and SOHO, didn't have the cadence or potentially even the size of Solar Dynamics Observatory. And SDO's goal is mostly to understand space weather. Its goal is to hopefully predict it. And in order to do that, they outfitted it with this little satellite with an ultraviolet explorer, ways to image the atmosphere of the sun in multiple ultraviolet wavelengths, as well as looking at the Doppler effect on the surface of the sun and being able to image the magnetic field of the sun through Zeeman splitting. So we're going to get some terminology, but the surface of the sun that we see in the disk in the sky, we call that the photosphere. And the photosphere is the surface of the sun from which the visible light appears to come. And that's defined as the location in the surface of the sun. We'll call it the surface, but it's not really a surface. The photosphere is about 100 kilometers thick, and it's still a gas. So even though it appears to have a sharp edge, the sun's size is so incredibly large compared to the thickness of the photosphere that it looks like a sharp edge. But the photosphere itself has edges that go out and appear to be darker, and it's called limb darkening, where the edge of the sun, or the limb, we should call the edge, the outer ring of the disk of the sun, we call the limb, appears to be darker. And that's because when you look towards the limb, you're looking at higher and higher elevation above the deeper portions of the sun. And as you go up in elevation from the deeper portions, it gets cooler in the photosphere. So therefore, since it's cooler, it is darker. So when we look in the center of the sun, or smack in the center of the disk, it looks brighter as well as yellower. And so that is because we're looking deeper into the into the sun, and so we see it where it's brightest. But the photosphere itself is where we get the visible light from the sun. All right, and the image that you're seeing here shows a progression of sunspots passing across the sun. And as we know, the sun rotates. So the photosphere is not a visible surface, and since it's about 100 kilometers thick compared to the sun's 700,000 kilometer radius, yes, you can't tell that it's an edge. So that's what we call limb darkening, and this image is definitely shows this. This image was an image taken of an active region, and we can see an enormous active region is seen by the SOHO satellite, or the solar, one of another NASA mission, and that huge looping object that's in the middle. These are all sunspots, and these are active regions, especially the center one, which back in the end of October in 2003 launched an enormous solar flare. And that solar flare had some problems here on Earth, and it caused some issues down here on Earth. So let's look at the sunspots and what they are. And sunspots are really critical things because they look like blemishes on the surface, on the photosphere of the sun. They're cooler regions on the surface of the sun, and they have these very strange and interesting shapes. And this image was taken by Alan Friedman, who's a very interesting solar observer. All right, sunspots appear darker because they're slightly cooler than their surroundings. And so slightly cooler still is very hot. It was just 4,000 Kelvin versus about 6,000 Kelvin for the brighter areas of the sun. And we can see that that material in the sunspots appears to be moving, but it's not like it's a hole in the sun. It's not like there's no sun in the sunspot. No, it's just simply much cooler. So in the same sense that if you look into a fire at a campsite, and you see that the coals look dark compared to the fire, you know that they're pretty hot, and you wouldn't want to reach in there and grab them. It's just that they're cooler than the surrounding gases of the flame, and so therefore you wouldn't want to. They look darker. Now, again, the sun is not on fire. It is just so hot that it glows, and the reason the regions are darker is simply because they are cooler. And the central region is what we call the umbra. And the umbral region is a place of extraordinary magnetic field strength, and it can be the sunspots themselves are where can be incredibly strong compared to surrounding the sun and compared to the Earth's global magnetic field. Sunspots themselves can last for a few days. Their appearance changes very frequently. They are dynamic objects. They change with time, and they can grow in size and then shrink in size. They can live for a few days or up to many weeks. And the outer portion we'll call the penumbra, and they always come in pairs. So sunspots come in two sets, where one set is magnetic north and the other set is magnetic south. So they come in pairs where one is a north pole and one of us is south pole. So we can imagine that underneath the photosphere, if you wish to imagine this, that there's some sort of magnetic, even think of those old bar magnets or those horseshoe magnets where one end is north and one end is south. And the magnetic field is poking out. And that's not a bad example because something like that is happening in the sun. Of course, there's no big old bar magnets inside the sun. It must be because of the flow of electrical charges deep inside the sun, where the magnetic field then is generated by this current flow, and that current flow then pops up through the surface. All right, also sunspots are enormously large. Most of them are larger than the Earth, and some of them can be even larger than Jupiter. So sunspots can be catastrophically large in size, and to see that they move and change and alter their appearance rapidly is really very interesting. All right, so this was another set of sunspots taken by Alan Friedman back in 2011, and we can see that some of these sunspots are really big. Remember that the Earth there's approximately 100 Earth diameters across the sun. So each of the sunspots that we're looking at, that were taken by Mr. Friedman, these sunspots are much larger than the entire Earth. These are huge sunspots. Okay. So you saw on the background, there is kind of a structure, a honeycomb sort of structure, and they have a special name. Those are called granules, and granules are the visible top layer of the convection zone of the sun. So we can think of the sun as continuously burbling and boiling, if you wish, but it still is gases. So those are hot gases that are rising, and when they're very hot, they glow. And when they emit their light, and they get to a place where they can cool off enough such that they emit light, that's when we see the light coming from the granule. But because it's a hot gas, if it emits light, then it cools off. If it cools off, then it'll sink because a convective flow, you have hot gas rising and cool gas sinking. So each one of those little nodules is actually the center of an upwelling flow, and the dark places between them are where the hot gas has cooled off and now it's sinking back down. And the reason it's redder as opposed to yellow is because it's cooler. And so it has emitted its light, it's emitted its heat to space above it in the solar atmosphere above it. And then it is now cooling off and sinking. So these things can be very, very, very large. These granules can be up to the size of a continent. They can be about 1,000 kilometers across. And so they move around and they provide the base of the photosphere. And basically the granulation that we see here, those are the things that basically are what we call the photosphere. So the granulation of the photosphere is it. So granules are therefore pretty small features, and pretty small is 1,000 kilometers, or about 600 miles across. And they cover the entire surface of the sun except where sunspots exhibit. But remember something, but each individual granule lives for only about 20 minutes or so. So you have this structure on the sun that's hundreds of miles across, 600 to 1,200 or 1,000 miles across, about 1,000 kilometers across, that rises up, emits its light, cools off, and then descends back to the sun. So this is an enormous, enormous, roiling, windy place because it's called gaseous. So you can think of these as upward welling winds, and that's a really good way of thinking about it. So the flow in the granules can be extraordinarily fast, and many miles per second, about 15,000 miles an hour. And they actually, because of that, will produce sonic booms at the surface. So there would be interesting waves that get produced because of how fast they move. And so they themselves will create waves of basically pressure waves, and those would be sonic booms. So these things are moving faster than the speed of sound, which is really interesting. Something about the size of a continent, a gaseous cloud, moving almost that's about the size of North America or larger, moves up or down at faster than the speed of sound. Really interesting. Okay, but then you can actually look at much larger structures, and these granules can be grouped into what are called supergranules, and they can be much larger than the Earth, and about 35,000 kilometers across, which is bigger than the Earth by a factor of, say, 4 or so. So 4 or 5 times the size of the Earth, and we see these large, large, large structures, and they're called supergranules. And so we can think of them as a basic, huge bubble upon which the minor granules flow. So there's bubbles on top of bubbles on top of bubbles, or more specifically, bubbles of bubbles. And so a supergranule is a bubble of bubbles. They tend to be much slower moving, but they also are gradually evolving too. So it's kind of a scale sort of issue, and we notice them by looking at a Dopplergram. And so this particular sub-image is a Dopplergram that shows the speed, basically the emitted light at one wavelength, and if it's brighter, it's moving towards us. If it's darker, it's moving away from us. And so you get a Dopplerogram of these large objects. And since this is the entire disk of the sun, we're seeing very, very, very large features that are bigger than the Earth. And so these large wave-like structures have granules inside of them, and then they move up, emit all their light, and then flow back down as a unit. So that's the granulation and sunspots of the photosphere, but they deposit their energy to another layer that's just above the photosphere that we call the chromosphere. And the chromosphere is cooler, as a cooler atmosphere above the solar photosphere. And the chromosphere can only be seen when there is a total solar eclipse, or you have some sort of spacecraft that it can block the light of the sun very accurately, and so that you can actually visualize the chromosphere. But the chromosphere extends above the photosphere. It is cooler, but still extraordinarily hot. And since it's hot, it will glow with this characteristic pink glow. And that characteristic pink glow is that of hydrogen. And that's what you're seeing in this image that Dr. Reddy did of the total solar eclipse back in August of 2017. You can't even see it unless the moon covers it during an eclipse. But you can see other things there too. We're not talking about the white sort of puffiness that's going around about it. That's part of the corona of the sun. I'm more specifically talking about that pink glow right at the rim of the moon, and not the pink glow that's off to the right-hand side. That's a prominence. I'm talking about that lightish pinkish glow that's all around it. That's the chromosphere, and it's chromos because it's a color sphere, and the color is pink. And the chromosphere is heated in these spiky storms called spicules, and we see them. These observations are observed by NASA's Solar Dynamics Observatory, the SDO, and we can see them near the North Pole. And so SDO gets a full view, and it's looking at ultraviolet, so we can see where the spicules are, and the spicules form. At high definition or high resolution, we can see that the chromosphere is primarily these spicules plus a dim glow right above. So the spicules are kind of like these upward shooting jets, and they change radically and over extraordinarily short periods of time. So we can think of them as almost vertically pointing tornadoes of hot gas, which is a good way of thinking about it. And those are spicules in the chromosphere. The next surface feature that we see are called prominences. And they're called prominences because, well, they're prominent. And they tend to be looping structures that lift above the sun and carry tens of billions of tons of massive material with them. So this is an example of the sun, I believe, that was taken by NASA. And this is amazing, amazing loop prominence that's extraordinarily large. Underneath that loop, hundreds of Earths could fit. It's a huge, huge, huge loop. All right, here's another example of an interesting prominence that was taken by the Stereo spacecraft, or I believe the Stereo or SOHO spacecraft, another NASA image. And it's basically a lifting gaseous bubble and loop that's coming off of the surface of the sun, and they're called prominences. And now we're going to look at it. I'm going to go and show you a couple of interesting prominences to show you how they move. And this series I'm going to show you in just a second. These prominences can be extraordinarily large, and they're guided by the magnetic field of the sun. So charged particles get in the magnetic field of the sun, they're lifted off the magnetic field of the sun, and they move as the magnetic field moves in the sun, and it's very dynamic and fluid. And as it does so, the charged particles flow on the magnetic field, and you get these kind of filamentary appearances to them as the charged particles fly along them at an extraordinarily fast pace. And I put the Earth in there just to help you see the approximate size scale of some of these things. So look again, as it zooms out, we see a series of spiky features, and those are called spicules, and the glow right above it, that would be the chromosphere, and the prominences are above that. Prominences tend to happen around sunspots, so there's a link between these active regions, which are the glowing region that you see there, and this is of course taken in extreme ultraviolet light. But if we were to look in that area in visible light, maybe say just normal light that we would see with our eyes, we would see a dark sunspot. So there's a difference in the view that we have of the sun when we look in ultraviolet as opposed to visible light. All right, so next thing we're going to look at is what's called the solar corona. And this was by Stan Honda. Stan Honda also went out to see the total solar eclipse, and he made sure that he got some beautiful, beautiful, beautiful images of the eclipse. And the corona is the gaseous material that comes off of the sun and streams out into space. So strictly speaking, the sun doesn't really have a solid surface, because where does it end? It really doesn't end. The solar corona is an extension of the sun. The photosphere is where most of the light that we see comes from, but the corona is only visible when the photosphere and chromosphere are both blocked. So you need a total solar eclipse in order to see it. And if you go to see a total solar eclipse, yes, you actually do see this in the sky. It's absolutely fantastic and gorgeous. But the corona itself is also rapidly changing and guided by the magnetic field, and is a product of the magnetic field of the sun. In fact, if we look at this thing on the right, we see that it has this kind of leaf sort of structure on the one that's pointing at 2 o'clock. We see it's kind of broad in the side and then it kind of pinches at the top. And that's kind of very common for appearances with the corona. Well, if we actually take a spectral analysis of the chromosphere and the photosphere, we can determine the materials that make up the sun's atmosphere. And this is a sample sort of thing that we might see. But if we were to actually go to the McNath Solar Observatory, which is down in Tucson, Arizona by the border, right at Kitt Peak, we find that a high resolution solar spectrum shows enormous numbers of spectral features, and simply by looking at all of these spectral features and taking out what we call telluric lines, which are absorption features due to the Earth's atmosphere, we can determine we can observe in the solar abundances and what exactly makes up the sun. And when we do that, we actually discovered that the sun's atmosphere is about 90% by atomic number, about 90% hydrogen, and by number about 9% helium, with very, very, very trace elements of everything else. So the action of all of those things is mostly because the sun's mostly hydrogen and helium, and all of the other lines that you see come from extraordinarily trace amounts of the rest of the elements. All right, so the solar atmosphere itself, if we look at the entire thing, it starts at the photosphere at about 6,000 Kelvin. The chromosphere is when it gets cooler. It transitions then into the corona, which then is another 10,000 kilometers up, or about 2 Earth diameters up, or about 2 Earth radii up. And then we get out into space, and it heats up enormously. It gets up to millions of Kelvin. So the corona itself is extraordinarily hot gas. It's very, very, very tenuous and visible in X-rays because of the temperature. But it's interesting that it actually has this temperature profile, and the study of this and why it cools down for the chromosphere and why the corona then gets so much hotter. That's an area of active research. So occasionally we don't see these things. And this is a view of the quiet sun when there's no sunspot activity and no prominences and everything like that. And that's all interesting and everything. And this is where looking at the sun in visible light. So we see invisible light at a specific wavelength of 6562.8 angstroms, which is in the red region of the sun. We see that the sun has that mottled appearance of the granulation, and we see a couple of tiny sunspots and very few spicules and very modest prominences. But this is what we would call a sun that has very, very, very quiet appearance to it. And sometimes we have magnetic fields and sunspots. So let's look at that in more detail. So how does the magnetic field of the sun create a sunspot? Well, the magnetic field is generated deep inside the sun, and occasionally the magnetic field bursts through the surface. And when it does so, it's doing to try to release energy. And so the magnetic field becomes tangled inside the sun as there's rivers of current, literally current rivers of electrons flowing very quickly in a literal current inside the sun, and that creates a magnetic field as a dynamo effect because of the differential rotation of the sun. So the magnetic fields get set up, and occasionally the magnetic fields bunch up inside of the sun and therefore poke through the surface. And when they do, the magnetic field lines, they have a direction to them, and the north end of the magnetic field and the south end of the magnetic field, where they puncture or at least go through the photosphere, that's where sunspots occur. So where the magnetic fields come through or breach the photosphere, they cool off the surrounding photosphere by giving a way for the particles to remove their energy. So they can flow along the magnetic field lines, and as they do so, they can emit energy and therefore cool off. Therefore, the sunspots are places where it's cooler. And so that's why you also get them in pairs. Why you have sunspot pairs is because they trace the magnetic field of the sun. So the magnetic field traps the gas and then allows the sunspots to be cooler and deep inside the convection cells, because remember, there's this roiling convection that's happening under the sun, and so we have all this motion of hot gas, which is essentially what we call a plasma, and a plasma is an ionized gas. And so if you have motion of an ionized gas, you're going to create electric fields, and electric fields in motion create magnetic fields. And so it's an incredibly complex interplay, which creates magnetic fields that then burst through, and that's the only way that they can go is that the magnetic field itself creates a loop. And then that magnetic field is invisible unless it has hot gases in it. And then those hot gases then can emit light in order to cool off as they move through the magnetic field. And that's what we're seeing here, is that as the hot gases move through the magnetic field, they cool off, and as they cool off, they emit light, and that traces the magnetic field. And so they aren't solid objects, and they're not things. Those are just filaments or rivers of hot gas that are charged particles that are flowing through these magnetic fields. All right, so now what's interesting is as the sun rotates differentially, there are times when the sun has a very even magnetic field, and then over time, the magnetic field is tied to the gas inside it, but the sun rotates differentially and so drags the magnetic field around and really tangles the magnetic field up. So occasionally you have magnetic field lines that then get parallel to each other, and as they do so, there's a pressure that happens between one magnetic field next to another, and in order to relieve that pressure, they poke through the surface to create those sunspot pairs. And that's what we're seeing here, a nice quiet sun where the magnetic field is all nice and regular, and then as the uneven rotation rate of the sun, slower at the poles and faster at the equator, tangles the magnetic field, eventually gets so tangled and all the magnetic fields get so close together that it's much easier to release that energy by bursting up and getting out of each other's way. In just the same way, when you have like toy little magnets, they really kind of jump away from each other when you push them together and want to go to a more even state or a more lined up state. And so this is the attempt of the gases in the magnetic field to kind of make a more lined up state. But there's incredible energy associated with it, and they can't do it, so the first thing they do is create a sunspot. So that means that solar activity changes with time, and you can go from quiet times to active times, back to quiet times, back to active times. So we have the solar activity changes with time, and how many sunspots there are changes. And if we look, we'll find that we can actually hunt for this throughout history. When Galileo first started looking through a telescope, one of the things he did was to stare at the sun. And you shouldn't do that, but he was drawing things and he didn't know. But it was very, very bright. But he did his own drawings of the sun and saw sunspots. And if you make an image, make a little movie out of the sunspots that he saw, then you actually see that there's 36 plus drawings, the 36 drawings that he did, shows that these sunspots move across the surface. Well, we don't see those sunspots today, we see different ones. And in fact, the sunspots that he drew changed from day to day. So the sun has a cycle that every 11 years, the sunspots begin at higher latitudes and then get more and more and more concentrated. There's more of them, and they go to lower and lower latitudes, closer and closer to the equator. So as a sunspot cycle occurs, you start from very few sunspots, then a few appear way at high latitudes, then more appear at lower latitudes, and they get closer and closer to the equator, and there's more and more and more of them, and then all of a sudden they all dissipate. And then you start again. So you can count, the solar cycle is a counting of sunspots, and this has been done for a very, very long time. And this is what I mean by that counting set. We can determine how you want to count them. It's like how big they are, how small they are, where you see them, and so forth. But if we see as time progresses that this 11-year cycle shows that sunspots there's for a very short period of time, we have a solar minimum, which is the minimum number of sunspots. Then you have a solar maximum, where there's a maximum number of sunspots. And then all of a sudden they go to the equator and then dissipate rapidly, and we get a minimum again. So this is the solar cycle. And in fact, it's actually a 22-year cycle because we switch magnetic polarities. It goes from magnetic north to magnetic south and so on. And therefore, the number of sunspots is every 11 years, but if you add in the magnetic polarity, it's every 22 years. And then there was an interesting time right after Galileo started looking called the Maunder minimum, where there were few, if any, sunspots. And it was not for want of looking, because people really were looking for them at that time. We'll get back to that in just a second. The solar cycle has been observed for an extraordinarily long time. We can see from here, from David Hathaway's work at NASA, that the sunspots are summarizing all the total number of sunspots throughout history. And he started his work looking at the historical place from 1750 and onward. And we can see there's been a number of sunspot cycles. And these are good counts of people looking at the sunspots for a long period of time. And if we then go back all the way to using Galileo's data and start from 1612, we see that sunspot counts have been fairly consistent, that this cycle has been consistent roughly since the year 1750. But there was a time, roughly around 1650 to roughly 1700, that's called the Maunder minimum, where there were no sunspots. People were counting and were looking for them, but saw none. And it actually corresponded to a time of cooling on the northern hemisphere. It's interesting that that would occur, but nobody really understands the nature of why that would occur and what the point of that is, or if there's any meaning to it. But understanding what the Maunder minimum is and how it actually influenced our climate on Earth for those 50 years, it's a fascinating study. So decadal long cycles in the sun actually do have influence on the sun, on the Earth. And so the solar cycle affects us here. Next to the last is some very interesting stuff. There's solar flares. Sometimes on the surface of the sun, on the photosphere, you get extraordinarily violent events where active regions, like this massive sunspot region that's smack in the middle of the disk of the sun, there's some really, really, really huge, massive active regions. Now we call them active regions because there's going to be flares, there's going to be prominences, there's sunspots. They're called active regions. And solar flares can be graded from various types, but one of the largest types are called X-class solar flares. And though if it's a logarithmic scale, and so if you have an X-type 10 or an X-type 17, it's an extraordinarily large output. And so what happens in a solar flare is the following. We can see that in this particular thing, that was the image from then, and these are the satellite images that were taken by the SOHO spacecraft in 2003. The green image in the upper left shows the visible light image, or at least an ultraviolet light image of the sun. It's an ultraviolet light image that shows the solar flare occurring, and the solar flare is a momentary brightness, or some brightness that occurs over the course of a few minutes. And it's enormously large areas. The total energy output that can occur in a solar flare, you can see up in the green, which is in the ultraviolet, it will be on the order of tens of billions of nuclear bombs, 100 megaton nuclear bombs, all at once over the size of an area much larger than the Earth. So you can think of it as one of the incredible large output of energy. And because of that, you get X-ray emission and you get gamma ray emission, and there's the temperature on those areas in the sun can reach 10 to 20 million Kelvin, which is actually hotter than the center of the sun, and you get nuclear reactions on the surface of the sun. So that's what's happening with the solar flare event that you're seeing in the green. Then the result of that is which is shown in the red and blue, which you see after the solar flare occurs. We see the corona in the background, which is kind of this constant sort of flaring out on the sides. But then you get this burst that occurs. When the flare happened, it emitted an enormous amount of material, and might be hundreds of billions of tons of mass that flowed out at nearly the speed of light out from the sun. And it gets to Earth in a couple of days later. And when it gets to the Earth a couple of days later, you get events, or even hours later, depending on how fast it's going, which can actually cause the sparkling that you see in the observing in the telescopes of the SOHO spacecraft. So we see a continual outflow, which is called the solar wind. We see the corona, which is the constant streamers that are coming out. And then we see the coronal mass ejection that was directed straight at Earth on that date. That caused a power outage in 2003. All right, so there's some sound here. Let's get rid of it. And now I'm going to use a NASA video, which is a really interesting video that shows a prominence and an eruption of a coronal mass ejection back in 2013. And we see the prominence that occurred on the limb of the sun, and there's the prominence occurring. You can see the spicules and the granulation on the surface of the sun, and we see the flaring contrast. But as the sun is emitting this material, it also had a flare. So The Solar Dynamics Observatory could only see the prominence and the flare occurring, but the rest of the imaging was taken by, of course, the SOHO spacecraft as well as the Stereo spacecraft, which are also orbiting the Sun. So the Solar Dynamics Observatory takes a small amount, and there you can see the link between the prominence and the SOHO spacecraft's observation of the coronal mass ejection that came off of the Sun after the prominence occurred. So it released materials deep into space on May of 2013, and now the SOHO spacecraft has a much broader field of view, and we can see the coronal mass ejection going out into space. And that's hundreds of billions of tons of material. The other Stereo spacecraft, which is away from it's trailing the Earth in orbit, so it gets a different vantage point, about a quarter of the way around the Sun. And we can see the coronal mass ejection from a different vantage point as it trails the Earth about a quarter of the way around. And we're looking at the extreme ultraviolet. And now we go to the green view, which is another view by Stereo. And this is what's called, the COR stands for coronagraph, so it's covering the surface of the Sun. And now we can see the coronal mass ejection from another coronagraph. So the coronal mass ejections can influence the Earth massively, and they come from these active regions of the Sun. Oh, and if you want to go see these things, go look up the Goddard Space Flight Center at NASA. Their visualization stuff is fantastic. So we see a link between prominences and coronal mass ejections. So what can we have as a problem with this? The largest solar flare known to ever happened in September 1st of 1859. And when the coronal mass ejection reached Earth, it actually wiped out the Earth's magnetic field. It was the largest possible a solar flare that's been known to have ever occurred in the history of observing the Sun. After this solar flare occurred that Richard Carrington saw on September 1st of 1859, the next day, the aurora was visible all across the Earth down to the equator. And normally it's only in high latitudes, way, 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 way north. But basically it erased the Sun's magnetic field, and the telegraph had recently been invented, and people could actually broadcast telegraph messages across the United States without the batteries, because the batteries themselves were blowing up. So they couldn't actually use telegraphs with the batteries. They didn't need to. The ground was charged, and so there was an enormous charge across transatlantic cabling. If a Carrington-class solar flare occurred today, we would have massive problems here on Earth, unless, of course, we chose to do a huge power outage across the entire United States in order to preserve our electronic infrastructure. And you should really know that everybody who does any kind of work inside the electrical industry knows what a Carrington-class solar flare is, and they watch spaceweather.com in order to understand this stuff. And the solar wind is therefore the particles that come off of the Sun. Usually it's huge amounts of material, but for a very, very, very short period of time, a coronal mass ejection can have an enormous influence on the surface of the Sun. But we can see from this graphic that actually what's happening is which is from NASA, is that the particles are being redirected. And why are they being redirected in general? Because the Earth has a magnetic field. And so here is a schematic of kind of the interaction of an active Sun creating a solar flare that has a prominence that's visible to it. That prominence, that activity creates a coronal mass ejection that then travels out into space, and if it happens to interact with the Earth, some of those particles go down into the Earth's magnetosphere, which is the blue area that we see in the upper right, and can give us aurorae and amazing geomagnetic storms. So the Earth's magnetic field protects us. It protects us from the solar wind, and it protects us. But the coronal mass ejections can actually plow through and wipe out the Earth's magnetic field for a brief period of time, allowing the particles to reach the Earth and form the aurorae that it can happen in like a Carrington-class solar flare. So without the Earth's magnetic field, we wouldn't be here. We wouldn't have modern technology. We have grown up in a time where modern technology is protected by the Earth's magnetic field. And so spacecraft that live outside the Earth's magnetic field have to deal with that. And some spacecraft have been destroyed. Not all. Thousands of spacecraft are up there, but only a handful have ever been truly wiped out by it. But if there's going to be a Carrington-class solar flare, every plane's going to be grounded. We'll probably have massive brownouts or power outages just so that the equipment doesn't get damaged, if that ever occurs. And so what's really beautiful is that the source of the aurorae, and this is a view from the International Space Station, as the solar wind passes through the Earth's magnetic field, it spirals along our magnetic field, just like the particles spiral through the magnetic field of the sun. They can spiral through the Earth's magnetic field, and as they bounce around the Earth's magnetic field, as they hit the Earth's upper atmosphere, they cause the glow in the sky that's called the aurorae. And it's a beautiful thing to see from the ground, but it's really fascinating to see from the International Space Station like this. And here's what solar flares can do. They can damage spacecraft. They can cause the Earth's atmosphere to heat up and expand and therefore actually cause drag on satellites and cause them to come down. It actually can harm satellites. We saw in the solar flare that there was all those sparkles. Those are protons that are coming at nearly the speed of light and can damage the electronics of a spacecraft. And it can also create currents in the ionosphere, which is which basically can disrupt GPS signals. It can disrupt radio transmissions. It can also influence aircraft satellites as well. There's all sorts of crazy things that can happen if there's cables underneath the ocean. You can have incredible ground effects from there. You can have currents in pipelines. So yeah, the sun can do things to pipelines underneath the ocean. It's amazing. So knowing space weather is kind of critical to modern society. So that's why it's done. That's why NASA has this fleet of spacecraft to understand the sun. So the solar wind mostly escapes through the coronal holes where you have where the magnetic field, where you see the loops and flares of the corona, but you see these streamers coming out. Those are the coronal holes where it's cooling from there and material is flying away. And the coronal holes can be seen because they're darker in X-rays, as the sun looks bright in X-rays, and the coronal holes are where the solar wind arises. And as the field lines loop back to the Earth, they're trapped. But if the field lines extend out into the outer solar system and out in interplanetary space, then you get those beautiful, beautiful coronal features, and then that's the origin of the solar wind. And the particles can go out, meaning mostly protons and electrons, accelerated to extraordinarily high speeds and can reach the Earth in a couple of days from 93 million miles away. Last time we were talking about the surface features of the sun. Now let's get down to the center of things, down into the core of the sun. So what's way down in the core of the sun? What are the conditions like in there? And we see from this diagram that it can be very complicated, but below the photosphere and below the chromosphere. The deep down in the sun, the conditions are really rather strange. So let's go see what's happening down there. All right, so the sun's interior, which we call the interior structure of the sun, is divided up into a series of areas. The photosphere is very thin with respect to the sun's thickness. But then there's directly below the photosphere is what we call the convection zone, and it's an extraordinarily deep thing, 200,000 kilometers deep or so. Below that we have an area called the radiation zone. It has nothing to do with like radioactivity. No, it is just where energy is transported via radiation, and that's about 300,000 kilometers, and the core itself has a diameter of about 200, or radius of about 200,000 kilometers. And the sun itself is divided up in these sections. The convection zone is where energy is transported primarily through bubbles of gas that are hotter and then rise through, and radiation is where energy transports this way. So let's actually look at the interior of the sun and what is down way deep in the core. All right, in order to understand the depth and what it is way down in the core, we have to rely on a lot of physics. And so here we go, the beginning of lots of physics in this entire series. The major aspects of physics that we're going to be talking about first are the law of gravity, Newton's law of gravity, F equals gmm over r squared, the principle of hydrostatic equilibrium, meaning it don't move, and the equation of state, meaning how gases behave with respect to pressure, density, volume, etc. macroscopic variables you might measure about a gas, and some source of energy, meaning, the sun's radiating light, so therefore it must have something to replace that energy in the form of light, and then that energy's got to get from wherever it is produced out to the surface such that it goes out into space as light. All right, so we're going to deal with these in the next series of videos, this one and the next two, in order to get there. But first, let's talk about hydrostatic equilibrium, which is a fundamental concept with respect to stable things. Hydrostatic equilibrium, blah, 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 blah. Hydrostatic equilibrium simply means that the sun isn't getting bigger or smaller. It's not squishing in on one side and then getting bigger on the other. It's pretty much stable in every way we can think, or at least as another way of saying it's really not significantly sloshing around. And as such, the sun, because it's in hydrostatic equilibrium and it's a big ball of gas, it takes the shape of a sphere. And so the best way to think about it is that the gravitational pull of all the gases, which has mass, gas has mass, people tend to forget that, but the gravitational pressure due to the weight of the gas must be balanced by the pressure pushing against that gravitational pull. So something's got to provide that pressure, and that pressure is the gas pressure. So gravity pulls all the gas in, and the gas itself provides pressure outwards. And so there's a balance. And in hydrostatic equilibrium, let's explain this now. The deeper you go, the greater the pressure must be. So the greater the weight on top as you go in. So therefore, the pressure counterbalancing it must be greater. And this equation that we see, let's read it out because it kind of helps to read it. And it's in the form of a calculus-based equation where we're saying the dP simply means a little change in the pressure. So that D means little change in, and the dr on the bottom is a little change in radius or depth. So there's a little change in pressure as it changes in radius or depth, and that corresponds to something related to Newton's law of gravity. And that's where that big G comes from, because that's the big G of Newton's law of gravity. The m is the mass of some element pushing down on top, and rho, that Greek letter rho that looks like a P, a kind of a funny shaped P, is the density of the material that has that mass of that region, and then r squared on the bottom is the distance from the center, so from the center of mass. So therefore, when it's in hydrostatic equilibrium, the balance in pressure means that it's not going to be pushing up or down, and it's not going to be sloshing up or down. It'll be all in balance, and so you can measure how the pressure changes with depth by simply knowing what the mass of a little element is in there, and its density, and where it is inside of there. So that's what we really care about. That's hydrostatic equilibrium. And it means that the weight that is pushing down on top of a little element is being pushed back up by the pressure from below. All right, so in hydrostatic equilibrium, if you kick the star just a little bit, what happens? Well, if the pressure dominates, meaning pressure outward, something below, then the star will expand. And if gravity dominates, it'll contract. So it depends on what you do. If the gravity then dominates, it'll contract a little bit, it'll expand, and therefore, that if it contracts a little bit, it'll go until the pressure then pushes back, and then the pressure pushes back and expands, and then it might then say, ooh, well, there's not enough pressure to hold the gravity, so they'll contract a bit. So there's this oscillation that then gets balanced out in hydrostatic equilibrium. And eventually, when you think about this, as it oscillates between pressure pushing out and gravity pulling in, eventually it settles down. And when it settles down, you eventually get a setup where then the core is very, very, very hot and very dense and really compact, and surrounded by a much, much cooler, much lower density envelope around the core. And that's kind of what you get after a relatively long period of time, where the hydrostatic equilibrium is established inside a star. So let's look at that really carefully, and we'll kind of see it one more time just for fun. And so we got the blue arrows representing gravity pulling in and the gas pressure pushing outward. And so as you go deeper, we started the whole thing, and we say as you go deeper, the pressure increases as the gravitational force increases too. So the deeper you go, the greater the pressure. All right, so most stars, so how does the pressure vary inside of there? What is the thing that says what the pressure is? And we can go back to old high school chemistry with the ideal gas law. And the ideal gas law is what we're going to use in order to determine the relationship between the pressure, the density, and the temperature of the gas inside the star. So that is a very good approximation to exactly what's happening there, because it's pretty much every particle inside of a star is just like a is essentially a single particle, and so we can use the ideal gas law as our for the incredible range of temperatures that are inside a star and densities that are inside a star. So if you compress a bubble of gas, the pressure goes up and the temperature goes up, and if you let it expand, the pressure goes down and the temperature goes down. And so those relationships of the ideal gas law exactly tells us how the interior effects go in the star. So the bottom two equations are equivalent. Let's look at the left-hand one. Those brackets mean the average of, or average pressure. The bracket around the row on the right-hand side means the average density. And the little m with a hat over it, or the dash over it, means the average mass of the particles of the gas. And kT is the expression of the energy of a particular particle in the gas. So K is the Boltzmann constant and T is the temperature. Now on the right-hand side version, we have the pressure again, but a pressure at a particular area, and V is the volume pressure of a packet of gas, and V is the volume of that packet of gas, and that's simply equal to the total number of particles in that gas times kT, which is basically the energy of each particle. So the pressure times the volume of a particular packet of gas depends on how many particles are in it, and their temperature is what the ideal gas law really says. So I broke it out here in a whole bunch of different ways to give you the exact definitions for each. And there's some things to play with, is to say what happens when you make something hotter. If you keep everything constant, what's got to happen? Let's say you keep the volume fixed and you make it hotter. You keep the total number of particles in the box the same, the volume's the same, you make it hotter, well, of course, the pressure goes up. If you apply greater pressure on the outside of the box and you don't change the volume, then the temperature must go up. And if you expand the volume, what happens? And if you add more stuff, more particles, what happens? And so you can play like a mix game and say what things can happen if you do this and then you do that. And the Boltzmann constant is a thing that relates it's specific to the entropy, means more specifically the ways that you can arrange the gas particles inside of the box is really what the Boltzmann constant comes down to, and that relates to the energy per particle at a given temperature. So the ideal gas law says you got particles in a box under pressure at a temperature. How big's the box? How many particles are in the box? And it relates to either all of them. And it implies that all the particles are roughly the same in size, or they can be averaged to their size scale. And that's what the ideal gas law says, that these particles, when they hit each other, they bounce off of each other, they don't transform, they don't become other particles, they don't stick, they just kind of reflect off each other. Think of them as billiard balls bouncing around inside a box. That's a good way of thinking about the ideal gas law. All right, so let's take the ideal gas law and apply it to this core envelope structure of a star, such as the sun. And the deeper you go into the star, the greater the pressure. And the ideal gas law says that if you put it under pressure, then it must be hotter and hotter and hotter. And so down in the core of the star, it's going to be extraordinarily hot, much hotter than the surface. And that's just what we expect. And the central temperature then, it's a really interesting question. What is the central temperature? How hot is it down there? Well, the central temperature has what we call thermal energy. And thermal energy describes, when we say thermal energy, we mean the average motion of particles inside the core. And the thermal energy has to be high enough per particle that it supports the weight of all the gas on top of it. And the only way for it to do that is for it to bounce around really fast. And by bounce around really fast, we mean move really fast. And if it's got to be moving really fast, it's got to be really hot. So if we equate that thermal energy, which is 3/2 kT, to a typical a typical proton, which is what most of the sun is made out of, down in the core, to the gravitational energy it has by being there, which is the gm m sub proton, which is a little p, and then compared to the entire mass of the sun, which is the m sub sun, divided by r sub sun, And so we're just saying the gravitational potential energy of a proton at the center of the sun, which is the right-hand side of the equation, and we set it equal to the thermal energy, the average thermal energy at the core of the sun. That's why the temperature sub C, meaning core, and then the little the O dot, which is the sun symbol. So we're saying, what's the temperature at the core? We know the mass of the proton, we know the mass of the sun, we know the size of the sun. And so if we put all that together, we get the central core temperature as about 15 million Kelvin, which is extraordinarily hot. Okay, so we then say, well, what's the pressure there? And we can justify the central pressure by saying, well, what is the pressure down there? And we can take that hydrostatic equilibrium equation and then merge it with what we call the mass continuity equation, which is the little one that I put there in the upper right. And those two things merge together and just put them together as like the total sun value. So replace the dP with the pressure C sub sun, and replace the dr with the radius of the sun, and replace the m with the mass of the sun, and the rho with the density of the sun, etc. And what we get is that approximate value that we have in this equation, which says the pressure of the center of the sun goes roughly like, and that's what those equivalent symbols mean. That's what those double twiddles or double wavy lines mean. This means the pressure at the center of the sun is approximately the gravitational constant, that's at g again, times the mass of the entire sun squared divided by the radius of the sun squared, to the radius of the sun to the fourth power. And that's a rough approximation by taking these differential equations that we would use in calculus and integrate through using a computer, in fact, and just assigning them their global values. And that gives you an enormous, enormous central pressure. And it's like 10 to the 16th pascals, which is, wow, a billion is 10 to the 9th. So it's 10 million billion pascals. And that is more than 100 million times the pressure at the bottom of the Mariana Trench. So, yeah, it's pretty high pressure. By comparison, at sea level, the normal air pressure at sea level is about 100,000 pascals, so it's over 100 billion times the pressure at sea level. It's pretty high pressure, an extraordinarily high pressure in order to support the weight of the sun on top of it. All right, so now we have the central temperature, we have the central pressure. Now we can measure the density of the center of the sun, and we can go back to the ideal gas law, plug that in, and determine the central density. And we end up with, if we plug in the central values for the pressure and density, we get for the pressure and temperature, and give it a typical mass, which is a mass of a proton, we find that the density is on the order of 150,000 kilograms per cubic meter. Now, gold has a density of about 10,000 kilograms per cubic meter, roughly, and so therefore it is 10 times more dense than gold in the center of the sun. But it's still a gas, which is really crazy. We think about gold as being a solid, right? And it is at room temperature on Earth. But remember, the sun stays as a gas because, well, it's so incredibly hot. And it stays as a gas even though the density is much greater than that of gold. And gold is one of the most dense objects that we know, which is really interesting. So the central density of the sun is extraordinarily large. And we can use these basic arguments to argue that this is what the central density must be and what the central temperature must be. And this was done well before, the invention of computers and computing algorithms that would compute the central density and so forth. So the core conditions are, well, the core is about a quarter of the entire radius of the sun. The temperature is about 15 million Kelvin, and the density, for more specific calculations, is about 151,300 kilograms per cubic meter, compared to the surface, or roughly the envelope, or maybe just the photosphere, which the radius is about 700,000 kilometers. The temperature is much, much cooler at 6,000 Kelvin. And the density is about 1 gram per cubic centimeter. So it drops off really rapidly from the center to the surface. So, yeah, it drops off by over approximately almost 100 billion times, or 100 million times difference in density. And that's just by comparing, using the ideal gas law, the equation for hydrostatic equilibrium, and the fact that there's no gaps in the stars, that mass continuity equation. And we just put that together, And that's what we get as some really basic things. And because this is just simply hydrostatic and some basics of ideal gas law, this was actually understood very long before understanding what the actual how this gets that hot and how it maintains that heat. All right, so let's actually look now more detailed, and if we then go in a more detailed description of, well, how does it drop from the core to the surface? Well, we know that it can't just go like, here's the core value and here's the surface value. It has to drop off in some way. So again, we start at the core. It goes through the radiation zone, convection zone, and the photosphere. And then we can just dial down and say, okay, the center is the central line, and there's a peak at the center. And so we see that most of the high density area is right at the center. The densest portion of the sun is it's extraordinarily high density, and then it drops rather rapidly about just at the outside the core. So the core itself is where most of the high density area is, and the envelope structure is right outside these peaks when it's very, very low density. So in fact, it gets to be about the density of the surface of the sun well at about halfway out the radius of the sun. So the density that's about halfway out the sun is almost the same as at the surface, the photosphere, which is interesting. So it's extraordinarily high density at the core and drops off rapidly once it gets outside the core. Now then we can say, how does it vary with the temperature? The temperature, however, more smoothly varies. It still is strongly peaked in millions of Kelvin from the center, and it goes out to about 6,000 at the photosphere. But yet you can see that the temperature drops rather differently. So between these two things, between the steep difference in density and the smooth difference in temperature, there comes a point when you have that could actually draw out convection. So convection is when you have a strong temperature gradient, but not a very strong density gradient. And then that is ripe for conditions of convection. And that's what we saw on the surface of the sun is enormous granulation and supergranulation, which is the convective cells. So what exactly is convection? Well, we'll get to that really soon. And what are the other things as well? All right, so how the sun transports energy in the core. It transports by light just simply bouncing from place to place, and that's the fastest way for it to get out. And then as soon as it gets up to roughly the surface or about halfway out, the convection starts to come in, where the best way and most efficient way to transfer energy from inside to out is that bubbles get hot and bubbles rise and fall. And so that's about 2/3 the way out from the center, or about 200,000 kilometers from the surface down. So that's how the energy is transported from the interior out. How do we know that this is even true? Well, we can actually look at the surface of the sun, the photosphere, and see that it's actually roiling, rising and falling. And then we can map how those roiling, rising, and fallings occur, and we see that the sun is actually kind of ringing like a gong. And that ringing is waves that start at the surface, go deep inside, reflect off the interior or higher density regions or higher temperature regions, and then reflect back to the surface. And so what this diagram is showing in letter A is that there are oscillations that occur on the surface of the sun, kind of like a spherical drum or a sphere, just kind of a ringing sphere. And the right-hand side image is saying that as the waves travel deep from the surface, deep down in, they get to a hot spot and then refract away from that hot spot. And that's very similar to what happens in a mirage in the desert. So if you have a very, very hot surface, like a road in the desert, you get this double image, and it's a refraction of light because of the change in density and change in temperature. And so waves of pressure can actually be refracted as well. And the different kinds of waves and how they are incident upon the surface gives a distinct pattern on the surface. How they go down through the sun gives distinct patterns of what wavelengths are allowed, and that actually allows us to map the interior. And that process is called helioseismology. And helioseismology is the study of the surface of the sun and its motions up and down. And in this image, which is taken by the Solar Dynamics Observatory, what we're looking at is a speckly sort of funny image, and the dark dots are upwellings, and the white dots are where the things are moving down. So this is what's called a Dopplergram. Okay, so we'll see it again. I think it'll loop. There we go, good, it loops. And the Dopplergram shows that the dots that are coming up, which are dark, are coming towards us. The dots that are white are going away from us. And in the center of this image is a sunspot. You can see that it's kind of stable. But look for a second at kind of the static-y sort of feeling of the surrounding areas. You can almost see what the granulation looks like, which is kind of the lumpy bits, because the white is going down and the black is coming up. So you got these kind of lumpy sort of objects. But then you might be able to discern sort of wave-like patterns inside of this. And in fact, with large computer algorithms, you can. So you can determine that over the large scales, you get extraordinarily big wave patterns that you can then map how they reflect off of the interior structure of the sun. And so Solar Dynamics Observatory has the capacity to see this Dopplergram across the entire surface of the sun. And the left-hand side of this image is a Dopplergram, but taken by the Solar Dynamics Observatory, and the right-hand side is the sun in visible light at the same time. And so we see that there's motion up and down with respect to the sun, and this can be mapped to the interior structure, and that allows us to determine the interior structure of the sun and say, ah, yes, the model that we just showed you in those other things, how the density and temperature maps inside, can have an exterior appearance. So motions on the surface are dependent upon the interior conditions, specifically the temperature and density. And that study is called helioseismology, and it allows us to understand the center of the interior of the sun. Not all the way down to the core, but to some extent it does. But the core is measured in a slightly different way, if it can be measured, because nobody's ever been to the sun. Nobody can get to the sun. You can't get to the sun, take a scoop. All you get is light. And so therefore, we have to be able to see the surface patterns and understand them. And so seeing those wave patterns on the surface of the sun and how they actually bounce around tells us about the interior of the sun. Today we're getting even deeper into the physics of things, because last time we were talking about the nature of the core of the sun. We talked about how there was a temperature difference between the core and the surface, and a density difference and a pressure difference. So that means that if we wish to understand exactly how stars work and why they do what they do, we need to go from their properties that we can observe, such as their surface, somehow down into the center. And that's what we call stellar structure, or the structure of the stars on the inside, not just their appearance on the outside, because the inside is different than the outside. There are no sunspots on the inside of the sun, and because, well, whatever they are, they're very different, and nobody's ever been inside the sun. But we can make computer models, and we use those computer models in order to understand what's going on. So what we do is we have to take the observed properties, such as the mass, which is m sub sun, luminosity, which is the luminosity sub sun, which is these little symbols, again, these targets with a dot in it that are subscripts, indicate that we're talking about the sun with this particular variable. And we can look at the radius, r sub sun, and temperature, t sub sun, and there's also a Greek letter rho, which looks kind of like a tilted p sub sun. So again, when we talk about these kind of variables, and those that haven't seen this before, this is a value of the temperature for the sun. And sometimes we can use it as a proportionality constant. Let's say something's twice the temperature of the sun or twice the luminosity. And we would just put a 2 in front of that. Or maybe it's 10 times the mass. We'd say 10 m sub sun. And that will be the mass of that object. But for the sun, it's just m sub sun, 1 m sub sun. So the 1 is there. But what we want to do now is we want to take these global properties, such as temperature, mass, radius, and luminosity, and density, and correlate them to the structure inside the sun and see how it's arranged inside. All right. Before we really do that, though, we have to know how stars shine, and we need to know how energy transports through them. Well, very simply, stars are shining, and not really shining, because shine means kind of like reflection. So let's also use the word glow. Let's glow, emit light. Mostly they emit light because they are hot. They are thermal blackbody radiation. In fact, specifically, what we mean by a thermal blackbody is that the surface of the sun, this enormous, enormous thing that's 1,000,000 times bigger than the Earth, and is a surface area, I forget what it's 100 times 4 pi r squared, maybe over 50,000 or 100,000, somewhere between 50 and 100,000 times the area of the sun, has roughly the same temperature. which is really, really interesting. So that the average temperature of the sun is very close from one side to the other. Doesn't matter where you pick it. And therefore, it's a thermal black body, meaning it's so dense that all the light gets bounced around and it becomes one temperature. Now, the heat from the sun, comes out of the photosphere. So that's the luminosity. The luminosity is the rate at which it's losing energy to space in every direction. And therefore, if they're going to stay hot, they got to make up for that energy by producing energy somewhere deep in the core. Because remember, we determined the core temperature is 15 million degrees. Where does that temperature come from? Just from compression? Well, that's what the temperature, we didn't say the gravitational force made the temperature. We said if gravity's pushing down on it, that must be the temperature in order for it to balance. Now, it could be that gravity's providing that temperature, but then things would change because it's emitting light. But for now, let's eventually just say, what's the current state of affairs? And so the basics of thermodynamics, and thermodynamics is a series of laws and rules, but the most important one is that heat always flows from hotter regions to cooler regions. Now, it's a funny thing is that what does that mean about like a refrigerator in your kitchen? A refrigerator in your kitchen says, I want to force the heat that is trying to get into the refrigerator away from this box. And so it's a heat pump and pumps heat away by various mechanical mechanisms and fluids that actually expand and contract under pressure, or lack thereof. So, but heat always flows from hot to cold, and so you must provide work in order for that not to happen. So, stars, it's hot in the core, it flows out through the cooler regions above it, and eventually the surface it gets radiated away as light, or other stuff, but mostly light, and we care mostly about light here. So thermodynamics says that there is a flow of heat from the hot region of the core to the surface, which is much cooler. All right, so how does it get from the center to the outside? And that's called energy transport. And energy transport is simply the way we say there are three ways in nature that energy can be transported. The first is radiation. And so you have a bunch of photons, and photons might carry energy. In fact, they do. Every photon, as we learned in previous lectures, is a packet of energy, and its wavelength is proportional, its frequency is proportional to its energy. So you can make a photon by some process, and then the photon goes from there to here, and it has transferred that energy from there to here, and that is called radiation. Photons just go from there to here and carry energy. The next way is you can heat up a bubble of gas and move it because it's buoyant from one place to another, from a cool place to from a hot place to a cooler place. So if you get a bulk motion of gas, like a big cloud or a big bulk gas ball, it'll go from below to above. Finally, you can do conduction, and conduction is it's not the atoms vibrating against each other, and as they vibrate against each other, they hit each other with the same temperature. So if you have somebody vibrating one right next to you, you kind of get wiggly yourself. And so basically conduction is the transfer of energy because somebody's wiggling right next to you, and you can't not wiggle unless with this person wiggling right next to you. On the subways I get on occasionally, and there's people that are like really annoying and they jiggle in their seats, and eventually I get up and leave. So they conducted their energy to me, and therefore I had to get the heck out of there. In any event, these are our three dominant ways, the three ways of transporting energy from someplace that's hot to someplace that's cool. Let's look at each of them. But first, we're going to say that we can see that they play a part in every aspect. So if you have heat from a fire, that heat can be transferred by radiation because the gases glow, and the glowing gas then can radiate its infrared light to the pan above it that's being held above it. Then that conducts from the outside of the pan to the inside of the pan. Heat is conducted by the motions of the metal in the pan, and then that heats the water by conduction at the bottom of the pan. Then bubbles form, convective bubbles, meaning a a bunch of some of the water molecules at the bottom become hotter than their surrounding, and because they're hotter, they rise up, and then they emit their energy at the surface where it's cooler and then sink. Or more specifically, they displace cooler stuff at the top, and then that forces the cooler stuff to the bottom because you just don't have big gaps in fluids. So the three equations to the left dictate those things, and they all show a temperature gradient. That's what that dt dr means, a change in temperature as a change in radius or distance. And this is specifically for stars, so we're thinking a vertical distance. So as the temperature goes from how does it vary from the in to the out? And these three equations show that. Radiation, on the first one, the kappa, the little k at the top, shows how light is absorbed or emitted. The rho and L are an indication of how far. Rho is the density, and L is how far the photon travels before it gets absorbed by the density of material. And the k, kappa, Greek letter kappa, shows how well it can absorb it. On the bottom, there's a surface area thing. Let's have that pi r squared thing. There's some number 64. The number 3 is just rho. Those things come about as a result of yada, yada, yada. I'll just say that. But that shows a surface area through which the radiation must pass. And the sigma t to the fourth, that little sigma, which is like an O with a hat on it, sigma t to the fourth indicates the amount of energy that you get in a black body. So it's assuming that the radiation profile of a little bubble of gas, or wherever the light is traveling through, it is the same signature as the material around it. So if it's transporting by radiation, then the light has the same temperature profile as the material surrounding it. And so therefore it's all the same thing, and it can bounce around quickly by radiation. Middle thing is adiabatic convection, meaning the energy does not flow into or out of the bubble, and so the temperature gradient depends only on the pressure, and as well as how well it can hang on to that heat, and that's what that gamma is at the left. So you have a pressure gradient, and the pressure gradient means dpdr, and there's a difference in temperature and pressure, which is the T over the P. If you have a pressure gradient and there's a temperature gradient inside of that pressure gradient, then you can get convection. Finally, conduction depends on how well how close the atoms are to each other, how close they are, and how easy they are to. If they're very, very tightly packed, then vibrations between atoms actually conduct energy more efficiently than the other two. So which one of these things are used is dependent upon the temperature, the pressure, and the density of the material in which you're discussing. And so whichever has the steepest temperature gradient wins. And it depends on the material that you're talking about. All right, in radiation, energy is carried away by photons coming from their heat source. Funny thing is, deep in a star, even though the density is greater than that of gold, 10 times that of gold, the temperature is so incredibly high that it still is efficient for it to transfer itself around by radiation. But just because it's transferring around by radiation doesn't mean it's like, boom, I'm out from the center of the sun. No, it bounces around incredibly. In fact, it only goes about a centimeter before it hits another atom and goes in some random direction. And when you're at the bottom of the sun, or the core of the sun, every way looks up, because every way is up. And so you have a random walk for this typical photon to go and interact for where it's emitted in some reaction that creates it. And it bounces from from nucleus to nucleus, or electron to electron, scattering off of them, bouncing off of them, reflecting off of them, transferring its energy around. And eventually that photon, after almost 250,000 years, makes its way to the surface. And that is called a random walk, or a drunken walk from the center outward. Once it gets closer to the surface, though, it tends to be bounced around instead by radiation, but through convection. And that's what we've seen at the surface of the sun. That's why I drew the arrow long toward the surface, but doing that random walk in the core. All right, so convection, though, again, is where you have a hot bubble that's close to a heat source, gets warm, becomes more buoyant than its surroundings. Meaning if something more buoyant means less dense. And so if you have some fluid where the density can change, And then if it's less dense, it becomes more buoyant. It can then rise as a result because it overcomes the pull due to gravity compared to the bubbles around it. And so the bubbles rearrange themselves such the hotter bubble moves upward and the cooler bubbles move down. Eventually, the hotter bubble gets to a place where it can transfer its energy more efficiently, say by radiation, and then it cools off and then sinks. So convection sets up flows or boiling flows and roiling flows that mean that you have bubbles rising and bubbles falling. And we've seen that at the surface of the sun with the granulation and supergranulation. All right, and convection is also very easily seen in a boiling pot of water when you make spaghetti or ramen noodles. Conduction, though, is when heat is passed by vibrating atoms to atoms in some dense material. Now, the funny thing is that this takes time. Now, it's very strange because you think, well, why can't it just radiate the heat? Well, apparently, it's so dense, the materials are so dense, that light can't go very easily from point to point to point. And so, since it can't go very easily because of the high density of the material itself absorbs that energy that may have become emitted by light or transferred by light, and it starts to vibrate, move, and glow. And then it starts to glow very like maybe an infrared, but then eventually the vibration of each atom or molecule or starts to vibrate against each other, and then that feeling of heat in your hand when you pick up a hot pot or something that's been next to a stove is because your hand is now getting vibrated, or the atoms in your hand are being vibrated at the same rate as the vibrations of the handle of the hot pot, and then you get a burn because you typically, if it's very, very, very hot, then you get boiled water quickly inside of your hand, and that damages your skin, etc., etc. So what you have to have is you have to have extraordinarily dense materials. And this does not really come into play in typical stars because even though it's extremely more dense than steel at the center of the sun, the temperature is so incredibly high that the atoms behave as a gas, not a solid. And so conduction typically happens in solids where there's a binding, where they're so packed together that electrons from one atom are in contact or shared with electrons from another atom, or electrons are shared among atoms. So how is energy transported in stars? In normal stars, it's a mix of radiation and convection. We've seen with the sun that it's convection at the surface, so I'm just going to say right now that it's mostly radiation at the center, and that's what it works out to be. And if you have, and conduction is not the way to go because the density where conduction happens is too low for the center of the stars, which is fascinating. So conduction is kind of this funny thing where it has to be not too hot, not too just right. It's kind of a solids thing, and stars are not solid, so you'll have radiation and convection. However, if we look at, say, white dwarf stars, which are extraordinarily dense objects, then light can't get through very easily, and so it behaves as though it's a solid, and then you have conduction that works. Anyway, so when you have stars roughly like the size of the sun, which is the middle diagram, you have the center radiation transport is how things go, but near the surface it's conduction. And very small stars, we haven't talked about the sizes of stars, but let's say the size of the star is, say, very tiny or up to about half the mass of the sun, then it's convective all the way through. And we have much more massive stars, say more massive than, say, 1.5 or 2 times the mass of the sun, then it's convective in the core and radiative in the envelope. And that happens because the density of these stars drops rapidly as in the outer regions, and the density in the center, in the core, is actually extraordinarily high. So we can see that the convective region changes with respect to stars. In short, we have thermal equilibrium in stars, and this is incredibly important to think about because thermal equilibrium means the heat that's coming from the center and that is radiating the surface is replenished. So in thermal equilibrium, the surface of the star is not getting hotter or cooler. The core is in general not getting hotter or cooler. And so somehow there is an equilibrium of stuff. and you have a temperature profile like we saw in the previous one where it's hot in the center and cool in the outside, and that is in equilibrium so long as something is producing that heat in the core. So therefore the generation, how much energy is generated by the star, is the star's luminosity, and the thermal equilibrium is a balance. So you can get more luminosity out of the star if you contract it. Because remember, if you collapse a star, if you collapse a gas, it heats up, and if it heats up, it emits more energy. And if it emits more energy, then it'll expand. And if it expands, it'll push the star out a little bit. And so there's a natural thermostat to it all. And if the star has expanded, then it will cool off and it will start to contract because gravity is always trying to pull on the star. It's really important to remember that this gravity thing is always pulling on stars, and that is ultimately the squeeze of nature. And as it squeezes it, that makes the star emit light in some way, and that forces the evolution of stars because stars must change because their luminosity means that they're radiating away energy, so therefore something's got to be happening down in the core. Somehow energy is made in the core. There's a hydrostatic thermostat, meaning that as light and energy is passing from the core to the surface, and it's being transported either by radiative processes or convective processes, it goes from the core to the surface, and then therefore you have this thermal equilibrium. And then there's hydrostatic equilibrium, which is different than thermal equilibrium. Hydrostatic equilibrium means that stuff is not moving up or down. It's not contracting or expanding. And thermal equilibrium means there is a balance between the amount of energy being produced and the amount of energy being emitted. So thermal equilibrium is energy production and emission. Hydrostatic equilibrium means nothing's moving up or down. And it comes into balance. And so the sun is in balance, and it's been around for a very, very, very long time. But because of the fact that there's energy being emitted, the star must change. All right, so that's a summary of it, but now we're going to go do some extra bits really quick, and it's not that quick, but let's look at it anyway. So we looked originally at the hydrostatic equilibrium equation, which is a pressure gradient, or how the pressure changes with radius, and that depends on Newton's gravitational constant, the mass of the star, and the mass of the bubble that we're talking about inside the star, the layer of the star, and the density of that layer, and the radius from the center of that thing. And then we learned that with mass continuity, that there's some sort of mass element, and it's at a certain amount of stuff, and there's just no gaps in stars. And then we can use radiative energy transport, we saw that before, and somehow energy is being produced in the center. So again, mass continuity says that there aren't any really big gaps. So if you went out into a star, if you somehow went, you would not find that all of a sudden, say 20,000 miles in, that there's like this huge open space where nothing's happening. No, there's always mass there. And it's not like it drops away to zero mass or something like that. There are no big gaps inside of stars. However, energy is being produced in the core and not above it. So I'm letting the cat out of the bag by saying it's nuclear fusion down in the core. And so this thing says what is the luminosity, or dl, or how much luminosity is produced at which radius, dr. A little slice of radius from the center going out, how much luminosity is being contributed to the total amount, dl, at each little onion skin level radial of distance from the surface. And so those E's are Greek letter epsilon, E minus E sub mu, which is energy produced by neutrinos. But the energy that is being produced by the center of the star is E. And where is that E? That little E epsilon is how much energy is produced at that layer by some means. Now, I'm going to let the cat out of the bag. It's by nuclear fusion. And we have different flavors of nuclear fusion that we'll talk about next time. And there's even more, because pressure figures in, opacity, how easy it is for the light to get out from there to there. What is the thing that presents it? Every one of these things is a function of density and temperature and composition. So all of these equations are interrelated. And they're interrelated, maybe it was produced by the proton-proton chain or cycle triple alpha, and opacity measures how easily light goes through the star. But pressure is important because that's the thing that relates them all together. And so we use the ideal gas law, which we talked about last time, in order to relate them. So with a combination of all of these equations together, and I added the adiabatic convection equation in here too, if we add all these equations together, plug them into a computer, and solve the equations simultaneously, looking for the surface features and try to see what we have at the surface, we determine some incredibly interesting things about stars. And so this set of equations here will tell us the nature of the sun inside by all these variables: temperature, density, luminosity, radius, mass, pressure, the amount of energy produced in a certain little area, the average mass of a particle, where it is there, how far a photon can travel before it scatters off of things. It's an amazing, amazing, amazing set of things. But it's interesting to note that we can take these 6 and maybe a couple more equations that will tell us everything about the star. It's really interesting. And some of the only inputs that we care about are what the luminosity of the surface is, the temperature at the surface, the radius of the star at the surface, and the mass of the star. And we plug all of those things in, and that tells us the internal structure of the star. So in a very real sense, it sounds pretty complicated, but actually it's incredibly simple. And these things are much simpler than, say, trying to figure out what's going on inside of cells or DNA. DNA is an incredibly complex thing. Biological processes are incredibly complex. But they cannot be broken down into these kind of simple equations with any degree of ease. But at least stars can be, and we can learn how stars work. So this time we're continuing our exploration of the sun and the sun itself, and looking at exactly what powers the sun and what makes it go. Last time we looked at thermodynamic equilibrium, we looked at hydrostatic equilibrium, and we learned that thermodynamic equilibrium leads to internal structure of the sun, and all these equations dictate that, where some locations inside the sun are convective and some are radiative, meaning that's how energy is transported. And which one dominates, whether it's radiative or convective, depends on the density and temperature and pressure at that location. And so the equations themselves dictate the internal structure. And the fact that the sun is emitting light and is emitting energy means that it must be changing. So how exactly is it changing? How long has it been alive? That's going to be the question for us today. So really, we're talking about energy production in the core of the sun. We're looking at that last equation from the stellar structure equations, little dl, how much in a little onion-sized shell around the center, how much luminosity dl is produced in a little shell of radius dr at a distance dr, r squared, r, and with the matter density of rho, which is that little p, and epsilon e is the total amount of radiative luminous energy, and E sub nu is the stuff that escapes by neutrinos. So what's being lost? What's being seen? How do we get light from the sun, and how long has it been doing this? All right, big question. How long can the sun glow or shine or emit light? How long has it been doing it? How long can it do it? What is this lifespan of the sun? It's a really important question because it has bearings on pretty much everything else in the entire solar system, including evolution of life on Earth. So, in order to know how long the sun has been glowing, shining, and emitting light, we've got to know 2 things. We have to know how much internal heat is there in the sun, and how fast is that heat lost per second as sunlight. Well, the second one is simply the luminosity, and we can measure that relatively easily. It's really tricky to understand exactly what we mean by internal heat, though. So internal heat is a lot of different things. How can you get heat? Is it just simply hot and that just simply emits the heat? Is there some process that creates heat? And then that heat can be then transformed into light by various physical processes, and then that eventually makes its way to the surface and it gets lost. We saw last time that the process of light transmitting through the radiative zones actually takes about 250,000 years to get out from the core. That's how dense it is down there in the core, that it takes an extraordinarily long time for it to get out. But 250,000 years is a long time, so how old's the Earth and all that kind of stuff, and that's bearing upon this subject. So let's actually go back to the early part in the 1800s when people were developing the concepts of thermodynamics and such things, because steam engines were being built. Combustion engines were being built. And so there was a massive study going on all across Europe and the Americas about exactly how thermodynamics worked and how heat interrelated with work. And that's everything we really want to know. So by the end of in the early 19th century and by the late 19th century and the early 20th century, way up to the latter part of the 1900s, or the early part of the latter part of the 1900s, there are pretty much two ways that things could have sources of energy. One is chemical energy. You either burn something or you blow things up. And so that was fast oxidation of materials, or you put something on top of a hill and let it roll down that hill, which is gravitational potential energy, or you whack it with something. You take two things that are really far apart and let gravity pull them together, and then you make a big boom, and that would be like a meteorite hitting. So essentially, those are your two major energy sources that were known. And if you look at the economies and what people did back in the 19th century in order to do that, pretty much everything was reliant upon that. The electricity itself had not been developed until as a viable option for a very, very long time. So basically, burn stuff, blow stuff up, or drop things off hills. And that's how bread was made in water mills, because as a river would go by, that would turn a paddle, and that paddle would then turn a grindstone. And rather than make horses do it, you make the water going by a river do it. And so bakers used to be right by, and smithies, or using whoever needed power, steady, reliable power, would put a mill right on the waterfront of a river. Anyway, so that was what internal heat could be supplied in the 19th century. And people at the same time, other scientists at the same time, were studying how old the Earth was. And this was a fascinating study. And people were looking at how the Alps were overturned and folded, and the rocks were folded, and then the uplifted rocks in the Rocky Mountains in the American West. And even in Manhattan, if you go around the island of Manhattan, you find up in the northern areas, you see that the rocks are tilted, and they're layered and tilted, so things have been moved. And if you look at layered sediments, such as sandstones, or where fossils exist. But most classically, as one of the great things, is the beginning of geology, is by Jim Hutton in Scotland, and he hung off of a cliff above the ocean called Sychar Point in Scotland. And what Jim Hutton did is he looked at all the layers and found that inside the layers, just off this coast, this place called Sychar Point, he found that there were rocks that had been laid down by lava, then rotated, and then covered in sediment, then worn down, and then lifted straight out of the ocean hundreds of feet. And that process must have taken thousands upon thousands of years. And basically, these inclined rocks that occurred everywhere, and were there because of geologic processes, because nobody at the time was saying, okay, let's be logical about this. People didn't do this. Aliens or demons or devils or gods didn't do this, because that's boring. And to actually say, well, these creatures came down and gave us this weird look to the Earth, it's kind of silly, because that's, in a theologic sense, it's not that silly, because that's the nature of creation. But in a geologic sense, actually trying to understand it, you would come up against the idea of, well, okay, I can't prove that aliens came here or giant lizard people came and rooted around in the rocks and did that. So let's actually try to get a physical solution that makes sense, that keeps it simple, that we can justify. And that's called science. Everything else is either called theology, mysticism, or metaphysics. All right, so the problem is that when we looked at the age of things, it was found that the age of the sun was only about, if you think about chemical reactions, only keep the sun shining for a few thousand years. And if you whack the sun with a huge amount of meteorites, that keeps it going for almost 1,000,000 years. But so if you even imagine that every now and then the sun gets hit by something the size of Jupiter or something, then the sun could last a few million years. But geologists are finding that the Earth had to be hundreds of millions of years old, if not billions. So there was a fundamental conflict that was developing in the 1800s about how old the Earth was. And most geologists were saying, well, the Earth is older than the sun. And physicists who were, very smart, said, no, you geologists must be wrong. You're just looking at rocks. We're thinking thoughts. So this was pretty much the attitude that happened in the time, and there was a definite lack of reconciliation because one group sat around and thought deep thoughts in big places, and other people went stomping around in the Alps. So in the 1800s, two physicists, Lord Kelvin and von Helmholtz, developed an idea by which the sun could turn gravitational potential energy into light. So if you start with the sun, as we did in the previous lectures, in hydrostatic equilibrium, and with the internal pressure balancing the gravity, meaning it's hot enough in the center that gravity can't compress it, you then say, well, okay, fine. The light from the sun is luminosity, and that's radiated away, and it takes away some of the the sun's internal heat, which means that as the heat goes, it gets cooler inside the sun. And since it gets cooler, that allows it to compress, because a cool gas, if you take a hot gas and cool it, it compresses. So now it's got a lower internal pressure, which allows it to compress, which means the sun itself contracts and gets smaller physically. It's not just a big thing, it gets actually physically smaller, the radius gets smaller. And so then when the gravitation contraction compresses the sun, it then heats back up until it gets to balance position, and so it balances itself out, and the outward pressure increases because it's hotter now deep in the core, and then hydrostatic equilibrium is then reestablished. And this cycle then repeats, and the sun gets smaller and smaller by about 32 meters per year. 32 meters per year. Wow, that's actually kind of it's an interesting and very quick compression, which leads to the sun only living for maybe 10 or 20 million years as its maximum. But this is called the Kelvin-Helmholtz mechanism for producing energy or producing light out of gravitational contraction. Basically turning heat into light, and you heat something up until it glows. And that's where the heat and light comes from, because you assume, as Kelvin and Helmholtz did, that all the heat gets converted into black body radiation, and all the energy of photons and light becomes unified inside of the sun because the sun's opaque. And since it's opaque, the light bounces around inside of the sun until it has the same temperature as the material, and the material and the light have the same temperature, so therefore it is a black body radiation, which is what is observed. All right, so how long does it take? So you can't glow and contract forever in the power, and if it does power that, then we can assume that the gravitational potential energy, which is the gm subsun squared over r, this is r of subsun. So this is the total amount of gravitational potential energy if you take all of the matter of the sun and spread it out to infinity, way out. And then just say, okay, now let's take all of this matter, pretend it was at infinity, and let it all fall together to form the sun. And so as it falls together, it loses energy. And that total amount of energy it can lose, going from infinity to as small a point as you like, is the gravitational potential energy. Now you take the current gravitational potential energy, which is the numerator of that equation, and divide it by the luminosity, the current luminosity of the sun, L sub sun. And that's the energy emitted per second. So this ratio says that the sun could only live for about 30 million years, which is nothing, which is really nothing. Very, very, very short time scale. But this is important for stellar, but if you think about it, this might be important for stellar formation, but not necessarily for keeping the sun alive forever. If this is the only thing that the sun or any star ever did, then stars could only live tens of millions or hundreds of millions of years at the most. All right. So by the late 1800s, Kelvin and Helmholtz then basically take a couple extra things. That the sun will shine for a little over 20 or 30 million years. And that it was even actually corroborated by Kelvin, because he went and looked at studies done at the difference in temperature between the surface of the Earth, or rocks at the surface of the Earth, and rocks deep in mines. And he assumed that the Earth was once completely molten. And if the Earth was once completely molten and cooled to its present temperature inside, he got an age of about 10 or 20 million years. And he said, it's a good estimate, so I'm on the right track. So the Earth's only a few tens of million years old, But geologists were saying, no, it's a lot older than that. It's about 2 or so billion years old. Kelvin and Helmholtz, from their high seat in academia wearing wonderful clothing, said, geologists are wrong. Nature says, you guys are wrong. And geologists said, getting outside is nice because, nice day. Get out of that place and go walk in the Alps and go look at the rocks. The problem is that not all of the physical processes that that nature did were known to Kelvin and Helmholtz at the time. They needed to be discovered. So let's take a second back and just say, what about, let's take one of the great things that happened in the latter part of the 19th century, and that is the great industrial revolution because of the discovery and the use of coal-powered burning all across Europe. And let's pretend for a second that we've got a coal-powered sun. So if you burn a kilogram of just regular old brown coal, that's about 25 megajoules of energy. Remember, one joule per second is 1 watt. So this is about 25 megawatts. If you burned 1 kilogram of coal in 1 second, you would get 25 megawatts. So that's a lot of energy. And we have coal plants across the country and across the world because it does release a lot of energy. However, the sun's luminosity is a little bit brighter. It's about 4 times 10 to the 26 joules per second, or 4 times 10 to the 26 watts. And at a total amount of 25 megajoules per kilogram, you'd have to burn up almost 2 times 10 to the 19th kilograms of coal every second just to keep up with the sun's luminosity, if the sun is powered by coal. Now, since the Earth has a mass of 6 times 10 to the 24th kilograms, at that rate, you would burn an Earth-sized ball of coal in about 4 days and 8 hours. Now remember, about 1 million Earths fit inside the sun, so the mass of the sun is about 1 million times that of the Earth, so that gives you only about 4,000 years. Wait a second, that matches what those creationists are saying the age of the Earth is. Maybe they're right about something there. I don't know. But, don't tell them that because they might glom onto it. Anyway, just go talk to creationists and tell them that the coal could power the sun. That makes it only 4,000 years old. You'll have a lot of fun. Troll them massively if you wish. In any event, 4,000 years is the length that you get if you want to have a coal-powered sun, and it doesn't work because everything that we know makes the Earth much older than a few thousand years. Okay, back in 1896, Henri Becquerel was on the forefront of research, and in 1895, Wilhelm Röntgen had discovered X-rays. And what he'd done by looking at naturally fluorescent materials and minerals. So Becquerel was investigating these fluorescent minerals, meaning something made out of uranium. If you take pitch blende and you compress it, it emits light. So these are fluorescent minerals that he thought were glowing because irradiated by the sun. And so what he did is he thought, well, it must be getting light from the sun and converting it into this light, so it must be sunlight that's doing it. So what he did is he was going to go outside and take a whole bunch of photographic plates with potassium uranyl sulfate and wrapped it with black paper. And he was going to expose them to the sun and then go and see what was done and see what the images were. So he put something like a ring or some images on there to see what would be imaged on the sun. Unfortunately, the day he was going to do that, it was cloudy that day, and so he left it all wrapped up, and he went, oh, darn it, my photographic plates are ruined because it was a cloudy day. Kind of funny, because he wanted to expose it to the sun. But he left them wrapped in black paper, and he said, oh, what the heck, I'll expose them anyway. And even though they hadn't been exposed to the sun, he found that there were images of the objects that he had placed in with the black paper. And so therefore, the uranium itself had emitted radiation, and without any external source of energy like the sun or dropping rocks on top of it or like coal burning or something weird. So therefore, Becquerel had discovered radioactivity. He discovered that a mineral actually emits light. So what he did then is he made an apparatus very similar, and people had learned a long time ago that there were different kinds of emissions from these objects, and this was the forefront of research in the latter part of the 19th century, is that if you take a charged plate with a plus or minus on charged plate, or a strong magnetic field, and then you take your sample that's radioactive, and you put it inside a lead container so it all comes out a particular hole, and then you have a charged plate with a strong voltage, or you have a magnetic field. The alpha rays, which are positively charged nuclei, helium nuclei, they will bend towards the negatively charged plate. in their path. And so they will veer off to the, like, up in this direction. And if they're beta rays, they're electrons. And so they will be attracted towards a positively charged plane. Notice how the alpha rays, though, go farther than the beta rays. And that's because alpha rays are helium nuclei. And as helium nuclei, they're made up of 2 protons and 2 neutrons, so they don't get affected as much. So their path is not changed. However, electrons are very, very light, much lighter than helium nuclei, so their path gets bent rather rapidly. Gamma rays, though, don't get bent by it. So what was discovered is that alpha rays are positively charged, beta rays are negatively charged, and gamma rays are not charged. And so they had these 3 different kinds of things, and they were based upon their electric charge. And this was part of the great discoveries of the latter part of the 19th century. All right. 1905, Einstein had his great year, and he published special relativity. And he found that mass and energy and special relativity are the same thing. And that's through the great equation E equals mc squared. And it says that it's possible to somehow transform matter to energy and energy to matter. And he basically said they're the same thing, and that's the nature of one of the discoveries of special relativity. So if you can somehow have a way of actually converting matter directly into energy or energy directly into matter, you can do this. So there's an equivalent amount of energy that resides in every piece of matter, that it can be released to this large amount by multiplying it by c squared to get you the total amount of energy that's stored in the matter if it is converted completely into energy. That's what that means. All right, so 1920, Sir Arthur Eddington examined someone else's previous measurements, F.W. Aston's measurements. Aston was measuring low mass elements like hydrogen, helium, lithium, beryllium, and so forth. And he noted that and Eddington noted that 4 protons have just as 0.7% of more mass than a single helium nucleus. So it's kind of funny because helium nuclei are 2 protons and 2 neutrons, but 4 protons have a little bit more mass than that, but a neutron's a little bit more massive than a proton. So what's going on that these things are actually, that a helium nucleus has less mass? So he said, let's say, do we take the Einstein's E equals mc squared, and he proposed then, let's take 4 protons, put them into 1 helium nucleus, and the remaining 0.7%, less than 1% of the mass, could be converted into energy. So Eddington said, well, what if you did this? If you converted it, then you'd have that. And he said that's a heck of a lot of energy, because if you take that if you have 1 gram of hydrogen, 1 gram, which is equivalent to the weight of a paper clip. In the internet era, well, there's no such thing as paper clips anymore in the internet era, so what? That might be like a sheet of paper or something, or half a sheet of paper is about 1 gram. So, paper, goodness, what? People even know what paper is because nobody does paper. Well, anyway, grams. A few receipts that you have to take when you go and use Apple Pay at a store or something. Anyway, 1 gram of hydrogen, if you convert it to helium, 0.07 or 7 milligrams is converted into energy, and that becomes 6 times 10 to the 11th joules. And now that's a lot of energy. That's so much energy you could lift 64,000 tons of rock to a height of 1 kilometer. That's how much energy you could do with that. So that is an incredibly explosive amount of energy that comes out of 1 gram of hydrogen. So Eddington said, well, this is a huge amount of energy. Maybe we can use this. And that was his publication called The Internal Constitution of Stars on October 20th of 1920. However, it wasn't accepted because one does not simply fuse 4 protons into a helium nucleus. And so how do you actually do that? There's really hard to do. 4 protons colliding at once is extremely unlikely. It was also shown that 2 protons together aren't stable because, well, they both have positive charged nuclei. So how do you get 2 things just to stick? And somehow, well, even if you do chance to get 4 protons together, somehow you got to turn 2 of the protons into neutrons. Where does that happen? And it's got to be extraordinarily hot with temperatures greater than 10 billion Kelvin to get them close enough to fuse together. So that's the 64,000 ton question. Well, actually 4 aspects to this. And so how do you fuse 4 hydrogen nuclei into a helium nucleus? And that notation that we see at the top there, the hydrogen nucleus, when we say 1 to the upper left, that means how many total numbers of particles there are in the nucleus. And then a 1H means it's just a proton. But 4He means 2 protons and 2 neutrons for a total of 4 particles. Whenever it says helium, it always means 2 protons. Now you can have 1 less neutron, so you can have helium-3, and you could even posit helium-5, but I believe that's extraordinarily unstable and doesn't exist in nature, as well as helium-2, which doesn't have any neutrons, which also doesn't exist in nature in any event. So this is a very difficult thing to do. So let's look at the first thing. Trying to make them collide and stick is very tough. Why? Because 2 protons have an electrostatic repulsion. They are positive charges, so they repel. Like charges repel, opposites attract, just like that old Janet Jackson song, right? So electrostatic repulsion is so great that the temperature is so incredibly high that nothing can happen. So what do these 3 equations say? The U sub 2, 1 means let's take 2 protons, number 1 and number 2, that each have a charge Q. And Q is the electrostatic charge on a proton. The Q1 is the electrostatic charge on proton 1, and Q2 is the electrostatic charge on Q2. And D is their distance between them. Let's say it gets down to as close as 10 to the minus 15th meters. Let's say that's our D for distance. The 1 over 4 pi epsilon sub naught is just the way we convert charge and distance into potential energy, and that's what the U sub 21 is the potential energy of taking 2 protons, number 1 and number 2, and bringing them to a distance of 10 to the minus 15th meters from infinity. How much energy is created by that? What is the potential energy of them pushing apart? It's a pretty big energy. So then let's say, we can then say what a kinetic energy is, and we say, well, imagine that what we want to do is we want to get the kinetic energy high enough such that they can get to that potential energy, so that all of the potential energy is converted into kinetic energy. And what would the speed have to be of a proton in order for it to get that close? And that gives us a speed, a kinetic energy. And if we set that, if we say, well, that's the kinetic energy we wish to have, we find this an extremely fast pace. It's a very, very, very high speed. But then we want to actually say, well, if we convert then the potential energy into thermal energy, because thermal energy is a representation of the speeds of the particles, we then set the potential energy, U sub 2, 1, to the thermal energy of the gas. And so we'd say, well, what would the average temperature of all these protons have to be in order for them to get as close, to have the capacity to get as close as 10 to the minus 15th meters, and that ends up to be about 10 billion degrees, or 10 billion Kelvin, which is a pretty high number. And it didn't seem like at the time that anything could actually get them that close. All right, so back in the early 20s, people thought, well, the temperature of the sun has to be on the order of 10 million degrees Kelvin, 10 million Kelvin, not 10 billion, so it's 1,000 times cooler than it needs to be. Well, George Gamow, who is pictured here, he's in his striking suit, was researching exactly, in 1928, was researching how subatomic particles escape from the nuclei of atoms, because, well, the discovery of radioactivity said we have alpha particles flying out, we have beta particles flying out, and they said, well, how do they get out of those nuclei? How do they leave the nuclei? So people understood that nuclei were being broken down and becoming lighter, so therefore chunks were missing. And they said, wow, there's a huge amount of energy that's coming out from these things. How do they get that energy, and how are they getting it, and where are they going? So they discovered that the amount of binding energy of a nucleus was extraordinarily large. In fact, it was too large for any random process to just say, now I'm out and gone. There was no classical way for things to bounce around inside the nucleus of an atom, thinking of it as like a hole in the ground, for them to bounce around laterally such they bounce around enough that they would pop out. So quantum mechanics comes to the rescue, and Gamow uses the recent ideas of quantum mechanics, which states that all particles are also waves and have a distinct wavelength. We can imagine that the barrier to get out is a finite one, meaning it has to have a certain amount of energy and is a certain barrier to leave the nucleus. And whatever that barrier is, we can approximate it by some block. And we say, imagine that the wave of the waveform of the alpha particle, for a brief moment, gets outside of the barrier. And just on the chance. So sometimes it whacks the barrier and it reflects off of it, and maybe some of the wave goes outside. But imagine if the entire wave, on the off chance, goes outside the barrier. Because it's a wave, it must be continuous. So if it does that, then it escapes. So that's called quantum tunneling. And quantum tunneling says there's an off chance probability, a distinct probability, that it just simply goes past the barrier, which cannot happen in classical physics, but it can in quantum mechanics. And this idea allowed him to say, well, this is how things leave nuclei, and it worked. So then in 1929, just a year later, there was a couple of students, other researchers, Robert Decourt Atkinson and Fritz Houtermans, said, try to put it in the other direction. See if you can do it by putting protons together with protons. And they found that using the concept of quantum tunneling, you can actually have them merge together to form the nucleus that is formed of a proton and a proton. They can get them that close together at the lower temperatures that are known, the 10 million Kelvin, not the 10 billion Kelvin, using quantum tunneling. However, that was still an unstable nucleus of 2 protons. So that was good, but it's not the complete story. Well, and this is what we call the Gamow peak, which is a very important thing. It's called, and this is what he was talking about, and this is what the other two were talking about, which are talking about Gamow and Atkinson and Houtermans were talking about, is that the Maxwellian distribution of the probability at the temperatures that we're talking about, say 10 million Kelvin, the probability that a proton has that energy is the red dash that's falling from the upper left down to the lower right. And so the higher the energy, the lower the probability it has that energy. That makes sense, because it takes the highest energy things are rare. So the Maxwellian distribution is what you expect to have for a particular temperature when the protons are at that temperature. Some have higher energy and some have lower energy. They don't have exactly the same energy. There's a distribution. But very, very, very high energies are extremely rare. However, with higher and higher energies, the probability of actually penetrating the quantum tunneling barrier increases, and that's what the curve going to that increases to the right says. The higher the energy, the higher the chance that you actually get inside and stay. And so if you merge these two curves, you get what's called the Gamow peak, which means at a particular temperature, for certain energies of protons can actually get in, and that they're roughly around 4 kT, which is roughly 4 times the temperature, 4 times the Boltzmann constant. So it's going to be a very, very high temperature, but the probability that this happens is still extremely low. But it just shows that there is a merging place where there is an overlap between the probability that they get through that barrier, which is the penetration probability, and the actual distribution of energies inside of the protons, inside of a thermalized protons field. So there is a chance, and that's called the Gamow peak, and that chance is really tiny, but it's there. So how often do they actually get there? How tiny is that chance? Okay. So at the temperatures and densities in the sun, and you can actually calculate it out, we find that a proton, as it's whizzing around at the temperatures of 10 or so or 15 million Kelvin, goes about 3 millimeters before it collides with another proton. It's a very short distance. And they do that every 5 nanoseconds or so. So a typical one collides almost 200 million times every second. So a proton goes 3 millimeters and whacks into the proton 200 million times every second in the center of the sun. A typical proton. There's a lot of protons in the center of the sun, so how often does this happen? Well, that's still not enough, because the Gamow peak is very tiny. So it's still so rare that it's got to do 10 to the 25th collisions before it has, on average, before it has the chance to tunnel into the other proton and do the fusion dance. So it's an extraordinarily rare thing, and it's extremely temperature dependent. And if you push the temperature a little higher, then you get more and more and more, the penetration gets deeper and deeper. So that's pretty good. So quantum tunneling is extraordinarily rare, but at the temperature we're talking about, at 10 million Kelvin. But it's just enough to provide what's needed. And let's see how that happens. All right, so what happens when they finally do stick? Okay, great. So Now we've got a mechanism by which we can say they finally can stick. So nuclear fusion says that like charged nuclei got to get close enough in order to fuse, and they've got to be at this temperature, and they've got to have quantum tunneling. So let's see what we got. Let's say they get close and we got some quantum tunneling going on and protons smack together. So we got a proton smacking together, we got the little flash of light, and so what happens? Well, a whole bunch of stuff flies out. And we've got a neutrino flying out, a positron flying out, and a deuterium atom or a deuteron, not atom, but a nuclei flies out. And the existence of the positron, the existence of the neutrino, and the existence of the deuterium nucleus had to wait until later until it was actually confirmed. But let's see what we get. All right, so a positron is an anti-electron, and that basically is the same thing as an electron with a positive charge. And if you look up what Richard Feynman says, you could actually even look at it as a positron as an electron going backwards in time, or a time-reflected electron. And that'll send you down a rabbit hole on the internet. But for our purposes, it is the same exact mass and is negative and has an opposite charge. And every aspect about a positron is the opposite of an electron. So when an electron and a positron meet, they annihilate. All of the energy, all of the matter that was the positron and the electron is converted into energy, and that energy is in the form of light, and that light is in the form of a pair of gamma rays. So it goes, because that two need to come out because of momentum concerns, but there we have it. So you have a gamma ray that comes out, and so you've got light in the form of gamma rays of high energy photons, and those photons bounce around inside there and eventually scatter and reduce and break apart and become lower energy by the time they reach the surface. So that's a beginning for how light can be created inside the center of the sun. So let's look at another thing, a neutrino. Neutrinos don't interact with anything. They just go foop out of the sun. As soon as they're created, they leave the sun. They just don't interact with anything. They are neutral. They don't do anything. They're gone. And the last thing is the deuterium nucleus. So a deuterium nucleus is basically a heavy proton. So you take a proton and slap a neutron on it. And so now the neutron itself, the deuteron or deuterium nucleus, the symbol could also be called 2H because it's one proton, but there's two nuclei, two atomic particles in the nucleus, so it would be a 2H. You can also call it a D if you wish. So the next step then is to smack a deuterium nucleus onto a proton, and we've got something. So this is what Hans Bethe in 1939 published. His concept was, now you can't really make two hydrogen nuclei stick, and nobody could, because the major thing is what I just described was the creation of the deuterium nucleus utilizing the weak nuclear force interaction, which creates the anti-electron and the neutrino. So everybody else prior to his work had been saying, well, how can we force the two protons to stay together? And Hans Bethe said, now, how about the first thing we do is once they stick, that instantiates the weak nuclear force, and that makes it turn into a neutron. So now, the new deuterium nucleus can now collide and do other things. We had this whole series of steps, and there's Hans Bethe really smiling because when he did this, he received the Nobel Prize for his advancement in physics. I believe it was 1967 is when he was awarded that prize. I imagine this is his picture from that time. All right, so what did he call? He called it the proton-proton chain. So the first step is you take two protons and smack them together to form a heavy hydrogen, which is a deuterium nucleus. And one of the pieces of output is an E+, or that is a positron or an anti-electron, and that mu sub E is an electron neutrino, or a neutrino associated with an electron. So that is the first step of the reaction. So basically this is a reaction chain. And so you take a proton and protons, smack them together, that's what the arrow indicates, and you get out a deuterium nucleus and a neutrino. And the neutrino indicates that the weak nuclear force has come into play. So the gamma ray, the neutrino itself then becomes, of course, we just described how the neutrino, it leaves the town, but the anti-electron merges with electrons that happen to be around and becomes a number. It smacks into an electron and becomes a gamma ray photon. All right. So now the next step is, because the proton is now shielded, the deuterium nucleus is a proton and a neutron. That shields some of the positive charge of the proton in the deuterium nucleus. So almost immediately the proton and the deuterium nucleus collide, because well, it can kind of come in from the backside and smack the deuterium nucleus where the neutron is, and that forms light helium. So, and then emits a gamma ray. So we can think of the helium nucleus as a light helium nucleus with 2 protons. That's what He stands for, which is helium nucleus. But it's got 3 particles in its nucleus, and so 2 protons and a neutron. But when it's created what we could call hot, and it's a resonant frequency, so it can absorb it at those temperatures. And basically it's created in an excited state, a nuclear excited state, and that allows it to emit a gamma ray. So it's very similar to the creating an excited state of an atom, like in the Bohr model, except there's no little orbits inside of a nucleus of an atom, of atomic nuclei. So there's just an excited state, and it emits a gamma ray. So now we've got 2 gamma rays being emitted, one from the first step and now one from the second step, and each of these things has to happen twice. So now we have 4 gamma rays being created. And then finally, we have the 2 light helium nuclei smack together, because now they can do that. But you have to have very high temperatures because there's positive charges, right? 4 positive charges have got to overcome it. And this is where the 10 million Kelvin thing comes into play. So now they've got to smack into each other. They form a helium nucleus. And the kinetic energy that comes out of them it releases 2 of the protons. They fall out of the nucleus, and you're left with a normal helium nucleus plus 2 protons coming out. So the only thing that we get out of here is we basically take the top 2 lines, do that twice, and you end up with the bottom line. So 6 protons go in, and 2 protons, and a helium nucleus comes out. So the net result is 4 protons in, 1 helium nucleus out, and some other stuff like light, anti-electrons, and neutrinos. That's the end result of the proton-proton chain, and that's what earned Hans Bethe the Nobel Prize. So this proton-proton chain occurs about 10 to the 38th times every second in the core of the sun, and those times you see inside this diagram show roughly the average time it takes between an interaction. So it's very rare for the first step to happen. It's extraordinarily easy for the second step to happen, and it's not as hard for the third step to happen, but it happens pretty quick. So in any event, this process every second converts about 4 times 10 to the 38th protons into helium nuclei every second, which means that about 6 times 10 to the 11th, or 600 billion kilograms of hydrogen is converted into pure energy every second. That's interesting. That's really interesting. That works out to be about 4 million metric tons, and that's or 100 billion megatons of TNT. That's a lot. So this is an enormous amount of energy. This process can actually duplicate the output of the sun, which is about 4 times 10 to the 26th watts, which is an enormous, enormous amount of energy. So that's how we know that what's going on in the center of the sun. So we can take this theoretical construct and see how much energy is in there. And we say, does this really happen? And how big a volume is this happening in? And we say, okay, the size of the core of the sun, I mean, that sounds like a lot, right? 10 times 10 to the 38th times each second. That's a big number. 10 to the 38th is big, but it's spread out. So if we then say how much it's being done over the volume of the core of the sun, it's pretty crazy. You say, well, how much power is being produced in the volume of the sun? We say the total power output works out to be about 275 or 276 watts per cubic meter. Okay, what's 276 watts per cubic meter? That's like 300-watt light bulbs in a large U-Haul box. So that's not a lot of power, actually, per cubic meter. And that's about the metabolism of a lizard. So it's kind of funny. The total output of the sun in the core, averaged out over the volume of the core, is really, 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 really small. So that makes it kind of fun. So the tremendous power output is because the sun is enormously large, not because it's providing a lot of power. So the volume in which this can occur is enormous. All right. So, but if we then think about what this is like, The largest nuclear explosion ever done by humanity was in 1961. It was the Tsar-Bomba that was launched, that was detonated by the Soviet Union in 1961. They were originally going to do a 100 megaton nuclear blast. They made it 50 because they were scared. And that is basically 1% of what happens in the sun's core for 39 nanoseconds. That's crazy. So the blast caused huge damage up 600 miles away. It could be seen the blast was felt 1,000 miles away. Every second the sun does this 100 billion times. That's an enormous output of energy, and it's very good that the United States and Soviet Union and everybody's trying to dial down the nuclear bombs because they destroy lots of things, and it's better to be alive than dead. So thank you for not blowing those up over everything, guys. So the proton-proton chain is a way of actually getting, so the mass difference is extraordinarily small. Is that enough to make the sun shine for a very, very long time? The mass difference is tiny. That's called the binding energy of the nucleus. It's a tiny amount of energy that's released, and there's a huge amount that's happening, but is that enough energy to make the sun last long? So let's actually analyze it. Oh, but first, there's another process that we can use called the CNO cycle, which uses carbon, nitrogen, and oxygen as a catalyst. I'll let you pause this and go over it if you wish to, but essentially that stars like the sun don't do this. The sun only does this for a little bit of it, but if for stars that are just a bit more massive, it accounts for a huge amount of the process of the sun. The proton-proton chain is for stars like the mass of the sun or smaller, and any stars that are even slightly more massive than the sun, this is the dominant path for fusion. In any event, so the lifetime of the sun, how much gets converted? So it's 0.7% of the material gets converted into energy. So if we took the entire mass of the sun and converted it into energy and divided by its luminosity, that would give us about 100 billion years, which is interesting. But the sun will only participate because it's not convective down at the core, it's radiative down at the core, because we know that from stellar structure equations, that so only 10% of the mass of the sun participates in this. So since only 10% of the mass of the sun participates in this thing, then it reduces to about 10 billion years, and boom, there we have it. The total age of the sun can be about 10 billion years, and the age of the Earth fits into that, and we know the age of the Earth from meteorites and from other things to be about 4.5 billion years, so therefore, but the total age of the sun is much longer than the age of the Earth, and boom, we've got it. Nature, therefore, is revealed to us as us mere mortals, because it's just an amazing amount of stuff. 4 million tons of matter is converted into energy every second. Is turned into energy, completely gone. The mass becomes energy. And so modern estimates of radioactive dating give about 4.6 billion years. If we look at meteorites such as calcium aluminum inclusions inside of meteorites that fall, specifically one of the great falls that happened in 1968 called the Allende meteorite, which happened in Mexico. That meteorite fall gave us huge amounts of data about the age of the solar system, and we now know the age of the solar system is about 4.567 billion years old, and that gives us a good time. So the age of the solar system is about half the total fusion lifetime of the sun, so therefore the sun can live for about 5 billion more years. So stars shine because they're hot, and to stay hot, they make up for the energy lost. They have to make it up for it. And there's two ways. First, the gravitational contraction, which still does occur, but nuclear fusion keeps it hotter because now we have a pathway in order to get energy out of the sun. And that nuclear fusion solves the age problem that came up with in the middle of the 19th century and would have made Lord Kelvin shake his head. So that's what we've got, the age of the sun. And let's see, so main sequence stars, we discussed this before. Wow, what are main sequence stars? Well, like the sun, they rely on the proton-proton chain, but more massive stars with much higher core temperatures do the CNO cycle. Here's an interesting question, though. Why doesn't the sun explode? Well, the fusion reactions are extraordinarily temperature dependent. And so think about it this way. If you increase the temperature of the core, well, the nuclei move faster. If they move faster, then they stretch into the gamma peak. The peak goes faster, which means that they quantum tunnel more frequently. If they quantum tunnel more frequently, fusion occurs more frequently. So if you have higher temperature, you have more fusion. But fusion, as we know, creates light. And if it creates light, it creates energy. And that energy then goes into making the core hotter. So if it's going hotter, that should lead to even more fusion. So why don't stars explode? Like big bombs. Why don't they go out of control? That's an interesting question. All right. So there's a thermostat. Again, we go back to hydrostatic and thermodynamic equilibrium, and we say when the core heats up, that leads to a higher pressure. The higher pressure means that the whole core expands against gravity, and that cools the core, which then slows the rate of fusion. Now, if it runs a little slow because stuff's running out or what have you, the core cools, which leads to a lower pressure. Then all of a sudden, gravity pulls things together, pulls it, makes it contract, and then that heats the core. Ideal gas law again, because PV nRT, right? So the total amount of material gets compressed, and if it gets compressed, it heats more. Contraction heats it, and increases the rate of fusion. That's a thermostat. That makes it so it cannot be a runaway explosion. So it doesn't happen. Also, it's a fact that quantum tunneling is extraordinarily rare to begin with, so actually getting the first reaction is rare, so you really have to push very hard. But the dominant thing is the hydrostatic thermostat, because the core of the sun can actually respond to pressure waves due to like waves of pressure that happen on top of it, and that's a rather rapid process. So in sum, energy is generated by nuclear fusion in the cores. It's controlled by a hydrostatic thermostat and regulated by the advancement of the quantum tunneling, which is actually what allows it to occur. So the energy is then transported to the surface by convection and radiation processes in normal stars, and we haven't talked about white dwarfs yet, but we will, and you can go Google around if you wish. But the energy generation is called thermal equilibrium. Energy is created, it makes its way to the surface, it's radiated, so more energy must be created because it's being radiated. And then hydrostatic equilibrium says things aren't sloshing around really hard, or more specifically, hydrostatic equilibrium says if you decrease the pressure, you compress. If you increase the temperature, you expand, and so you decrease your temperature. So these two sets of equilibria merge together, utilizing the energy sources of nuclear fusion and to some tiny extent gravitational collapse in order to generate energy in the star, in our sun. So that's how the sun shines. The sun shines through fusion in the core, and it can live for 10 billion years, not 6,000, 10 billion years before it runs out. Fascinating stuff. And that shows, and all of these things are basics of modern physics. And that makes the sun a core area where we can study and test the nature and understanding of particle physics as well. Next time we'll see exactly how that went haywire just a little bit. We're going to finish off the sun this time. We've been talking extensively about the sun in the last few lectures. We talked about what's happening down in the core, nuclear fusion, the surface, prominences, solar flares, everything, how energy gets transferred inside the sun. But really, the biggest question is, how do we actually know that fusion is occurring in the core of the sun? That's a really important question. And the answer is an incredible form of detective work that happened in the latter part of the 20th century, and it was an amazing discovery set. And the answer is, look for the neutrinos that have been putatively created by nuclear fusion reactions. Nuclear fusion should produce neutrinos, and so let's go find them. And that was the mission for basically the test whether or not fusion actually is occurring in the core of the sun. All right, so let's go back to the nature of stellar structure and how stars are formed. We have a very, very, very dense place in the core of the sun where it's extraordinarily hot. The outer regions no energy is being produced, so it's just simply hot, hot, hot in the center. The surface areas are convective for the sun. Deep inside, energy is transferred by radiation. But the core of the sun is where it's hot, and it's been actually determined simply by using ideal gas laws as well as Newton's gravitational law, and that tells you that the core of the sun has to be extraordinarily hot, around 15 million Kelvin. And if it's hot enough, then fusion reaction could occur in the core of the sun, and the thing that would allow it is quantum tunneling into and out of the core as a function of the nuclear process. So nuclear fusion may be occurring in the core of the sun, and that little equation there, which is the rate of luminosity, dl/dr. dl is a tiny amount of luminosity at a small radius, dr, and that's equal to, if you think of a shell centered on the surface of the sun, that's at 4 pi r squared. And then the depth, rho is the density, and then E minus E nu is the epsilon, is the energy produced in light, and then E sub nu is the energy produced in neutrinos. So the luminosity of light depends on the density of material that's producing it times the energy per density, the energy per unit density. So energy production. So we will know that a huge amount of energy is lost due to neutrinos. So if we can just find evidence for it, it will show that it's happening in the center of the sun. All right, so again, what are neutrinos? Neutrinos are these are subatomic particles. They're fundamental particles. They don't interact with anything, or basically not at all. They're almost completely massless. They travel very close to the speed of light. Not exactly, but they're very, very close to the speed of light. They do not interact using the electromagnetic force. That's why they're weakly interacting. The little neutrino means little neutral one, and so it has no charge, no electric charge. And so they can interact through the weak nuclear force, which is itself is really not very interactive. So, and it doesn't bother with the strong nuclear force. Gravity, sure, but they're extraordinarily almost massless, so what the heck. Therefore, they can pass through an enormous amount of material without interacting with anything. A block of lead, 1 parsec thick, they could go straight through and not see a single atom of lead. So neutrinos are created, therefore, or at least we think they're created by nuclear fusion in the core. Every theory about nuclear fusion says they should be. And so therefore, if they are, they would simply stream out of the sun at or near the speed of light. All right, so let's take it really far back and say, what do we mean by fundamental particles? The standard model of particle physics says that there are basically 3 generations of fermions, of matter. There's 3 different kinds of matter. And these things are constructed to create them. In the first generation, you have the up and down quark, which combining together give you either neutrons or protons. But at the bottom are the leptons, which are fundamental particles. And the fundamental particle that we're really concerned about is the electron neutrino. So if a proton is converted to a neutron, or a neutron is converted into a proton, an electron neutrino or an anti-electron neutrino is involved. The other generations of matter, which are charm, strange, top and bottom quarks, give off different kinds or interact with each other and give off different kinds of neutrinos. And so there are 3 different kinds of neutrinos in all, the electron, muon, and tau neutrinos, and each of them has their corresponding object. The electron itself is a fundamental particle, so is the muon, and so is the tau-on. And over there on the right-hand side, those are the force carriers. So you've got the photon, which is a gamma, a gluon, which is a strong particle, a strong force particle. And then there's these 4 different kinds of particles that interact with the weak force. The Z0, which is the weak force particle that's interacting with the neutrinos, as well as the weak force that has a charge, which is associated with the electron. So those things you would encounter extensively if you went and took graduate, all this whole page. This page you would encounter extensively if you went to graduate school for particle physics. So let's just say that up and down quarks make up protons and neutrons, and electrons have as a pair the electron neutrino. So let's go hunt for those. Anyway, so now, remember back when we talked about the proton-proton chain, in 1939, Hans Bethe published that paper that talked about how stars would form hydrogen into helium via the proton-proton chain. And basically he said that his major step was that he said, oh, deuterium would be formed. When deuterium is formed, there's an anti-electron, which is that beta plus, and then there's a neutrino, which is that little kind of V type of thing that I've indicated in yellow. So the conversion of one of the protons into a neutron involves the weak nuclear force. So if the proton-proton chain is actually happening, then neutrinos should be streaming out a lot. How much? Lots and lots. In order to have the luminosity that we see of the sun, it must be happening 10 to the 38 times each second. This process. It's an enormous amount. Well, there's a lot of stuff down in the core of the sun, but still, that's an enormous number of interactions. So 10 to the 38th, which means that 2 times 10 to the 38th neutrinos must be escaping from the sun every second. So if we take those neutrinos and think of them as being spread out evenly over, that are coming out in every direction randomly, so we should think that they're coming out as in waves and as just like a circular in a spherical distribution going out in random directions, so they'd be smoothly distributed over the surface of a sphere. And if we think of them as being distributed over the surface of a sphere, then by the time the neutrinos spread out to the Earth's orbit around the sun, then we should expect to see over 7,000 billion neutrinos hitting every square centimeter on the surface of the Earth. That means if you hold your thumbnail towards the sun, every second 7,000 billion neutrinos go through your thumbnail. That's really crazy. So that's a lot of neutrinos coming out of the sun. So let's see what else that means. So really, 7,000 billion neutrinos through your thumbnail every second? Well, where does that number come from? Well, so if we think that the total number, there's these, basically the proton-proton chain and why there has to be 10 to the 38th comes from computer simulations. And those computer simulations say, okay, we're going to be saying that hydrogen fusion is the dominant energy source and it's using the proton-proton chain. And we look at the size of the sun, we look at the mass of the sun, we look at the surface temperature of the sun, we look at the luminosity of the sun in visible light as an ultraviolet and infrared. And then we think about those things. We take the surface conditions and we say, what would happen if that's the case down in the core? And you take this information and you put it through the equations of stellar structure and you make a computer simulation. Those computer simulations then say, well, the core has to be radiative, meaning energy is transported radiative, and the outer surface is convective. You assume that the star is not getting bigger or smaller, and you assume that whatever energy is leaking out from the surface must be being replenished at the center. Since the star is not getting bigger and smaller, that's called hydrostatic equilibrium, and that thermal equilibrium means that all the energy that comes out at the surface must be being replenished continuously by energy being produced at the core. That's what thermal equilibrium means. And if you combine all this together, you get neutrinos. You say, well, neutrinos seem to be a byproduct, and let's see what their energies are. And you can actually make a prediction, more specifically, what the energy of the neutrino is. Not just that there are neutrinos, but how much energy they have as they come out, because they get a kick. As they come out of this reaction, they get a certain amount of kinetic energy that they have when they leave, and that particular amount of kinetic energy determines both their speed as well as their relativistic mass. In any event, so the hunt was on, and the detection of neutrinos is really hard. So initially, people said, let's take some very heavy materials like gallium or heavy water or something like that. You get a lot of material, and you really need to work underground because there are cosmic rays, meaning there are things that also create neutrinos high in the Earth's atmosphere. Also, there's cosmic rays, meaning high energy particles hit the Earth's atmosphere that create high energy these particles then can hit the Earth and cause nuclear reactions. And you want to get away from those nuclear reactions. You want to get away from things that like protons and carbon nuclei and so forth that shower down from the atmosphere. And so in order to do that, you put it below the Earth and very far down. And so experiments have detected them. So let's see what we see. Okay, so that's kind of giving away the store at the beginning. How did they do this? The first one, well, there were others before this, but the first serious one was the Homestake Mine neutrino detector. So Raymond Davis, Dr. Davis, designed this, and John Bacall created theoretical background for it. And so the two of them worked together in order to see what happens. So Bacall said, let's look at all these equations, make computer simulations, and make a big prediction. And Raymond Davis built this thing that you see over to the side. And it ran from 1970 to 1994. And there was a gold mine down over in South Dakota named in the town of Lead. So there's a lead gold mine in the town called Lead in South Dakota. And so what he did is he went down about almost a mile down, and he took this enormous tank, about 100,000 gallon tank. He filled it with dry cleaning fluid. Dry cleaning fluid is perfect because it has some chlorine, and chlorine could react with it and turn to argon. So when the neutrino would hit a chlorine atom. The chlorine atom has a larger impact area than, say, a hydrogen nucleus for a neutrino, and it might react with it and turn into argon. So when the argon is then created, what they do is they have a tank, and the argon is a gas, so they drain the tank and count how many argon atoms they found. Now, that sounds like a huge amount, but they actually did this, and it was an incredible undertaking in order to do. And what they found was weird. What they found was that Bacall said that there should be a certain amount by all his predictions and computer models, but Davis's team, through that entire 24-year history, found only 1/3 of the neutrinos that Bacall predicted. So there were where were these other 2/3 that Bacall had? Now, just to give away it again, this is a major discovery that they actually found them. But others, they were awarded the Nobel Prize as well, along with other researchers that we'll discuss in a second, in 2002 for this. Anyway, this led to what we call the solar neutrino problem. Because if this was happening, where are 2/3 of the expected neutrinos? That's a pretty big gap. So where are these missing neutrinos? Because everybody thinks, it's like, what could possibly do it? So there must be something down there. So there isn't like a black hole in the center of the sun eating neutrinos. No, they're still coming out. They're being detected. But that's the key. All right, so there was a Kamiokande experiment, and I've shown here the super Kamiokande, which is an upgrade to that. But the Kamiokande experiment was basically a huge steel tank, and it was filled with incredibly ultra-pure water. And this ultra-pure water would have a different effect. So what you have, this enormous tank, and all those bubble things that you see there. And this picture, of course, is from the Super Kamiokande group. And this is from a deep mine about almost a mile below the ground, about half a mile below the ground in Japan, in the Kamioka mine in Hida City in the prefecture of Gifu in Japan. And so what they did is an enormous amount of water, and it had to be ultra pure for a reason I'll show you in a second. But all these photomultiplier tubes, because you have almost no light being from, so these are detecting light. And how do we get light out of this? So they basically are looking for them, and you drain the tank and float around and fix the bulbs if something goes bad, and you always check on them. So it's a pretty tough operation. So there's another view of it, and so there's all sorts of amazing views on. So the inside of that tank is interesting. Also, I got that nice little raft to do their maintenance. So here's how it worked. When a neutrino entered the huge, heavy, pure water, the neutrino would, say, hit an electron in the water, in the oxygen nucleus, and that would cause a recoil action. So the neutrino would hit it. It would be like a billiard ball that's going almost the speed of light, whacking this electron. The electron then would be ionized from the atom and speed away with a huge amount of energy. Now, if an electron is moving inside a medium like water at faster than the speed of light in water, you get this interesting effect called Cherenkov light. And Cherenkov light is produced by a particle, a charged particle, moving inside of a medium that is faster than the speed of light in that medium. So you get this strange cone ring effect. Another way it can happen is that the neutrino could collide with a proton and a neutron, and when it collides with both, that would create an electron or a muon, and that too would have an enormous amount of energy and form this Cherenkov light. So basically, it would carom off something and cause it to go faster than the speed of light in water, not in a vacuum, in water. And so there's the trick. And when it did that, it creates Cherenkov light. And funny enough, Cherenkov light is actually seen in nuclear reactors. And this is a view down into a nuclear reactor, like a fission reactor. And we see this blue glow around the control pile. And that blue glow is from the neutrons that are being emitted in copious amounts from all of these, say, the uranium in there. And the neutrons are going faster than the speed of light in water, and that's the blue glow of Cherenkov light. And the explanation for that blue glow was because of that. Anyway, so here's what the Kamiokande experiment can do with all those photomultiplier tubes. So this image that you see, all the little gray dots in the background are all the photomultiplier tubes, and you get this ring effect. And so the width of the ring that you see in there If it's going really fast, then the cone will be narrow and it'll make a small ring. If it's low energy, the cone will be wide because then it's not traveling as fast. And so you can determine both the direction from which it's going and its energy. So that's what's interesting about the entire experiment. And so they were able to find what the energy of it is and what the direction is. Now, if they're extremely high energy, they would probably be cosmic rays. The predictions were that lower energy ones would be coming from the sun by comparison. So they were able to detect the direction and energy. All right, so now here's the trick, is that it was thought of, is that apparently in 1967, the Italian physicist Bruno Pontecorvo figured out that the various neutrinos could actually transform one into the other. So they basically were almost the same thing. Electron neutrinos, muon neutrinos, and tau neutrinos. They're almost the same thing. So their quantum state can change randomly from one to the other as they travel through space. And so as they travel, there's a chance that as through empty space, they could travel. And that idea was proposed by Bruno Pontecorvo back in '67. This was then used and looked at more carefully by three physicists, Stanislav Mikheyev, Alexei Smirnov, and Lincoln Wolfenstein, and they developed the idea that neutrinos could transform into each other more easily in the presence of matter, just in the same way you get that Cherenkov matter, and it can actually, if it's close to some sort of electric field, which a matter has, then the neutrino might feel it some more, and that allows it to transform. So that the quantum state of the neutrino could change more easily if it passes through things. And so you can take a prediction of how fast it would, the predictions were made as to how fast it could change and how quickly it could change. And the sun's really big, and the sun's got a huge amount of mass, so it's possible that as the neutrinos would leave the sun, that they would transform, say an electron neutrino would transform to a muon, or a muon would transfer a tau, or tau back to an electron neutrino. So they would all transform into each other. And so they would, and this is what's funny is that the different neutrinos are called different flavors. So there's the flavor of the electron neutrino, the flavor of muon, and the flavor of tau neutrinos. And so if they would transform, they could transform out. Anyway, since the experiment could tell the differences, and they could tell the difference between the high energy ones from cosmic rays and the lower energy ones from there, they could figure out whether or not they were transformed as they were passing through the Earth as well. So they used this effect called, because of the three physicists, it was called the MSW effect. They looked through this MSW effect, and they initially found it with cosmic rays, because the cosmic ray neutrinos would also pass through the Earth, but cosmic ray neutrinos from the atmosphere very close to the mine would not transform because it wouldn't be passing through that much Earth. But the MSW effect was found for cosmic rays passing through the Earth. So it confirmed the MSW effect was real, so the neutrinos could actually transform. So that's interesting. And then what another group did finally is discovered the Sudbury Neutrino Observatory used heavy water, or water where one of the atoms is hydrogen. So they used a particular kind of water where one of the hydrogen atoms is deuterium. And this allowed them to detect all three flavors of neutrino directly. And so in 1999, they turned it on, and they turned it off in 2006. So this is really recent. I mean, this is talking the last decade and a half, 2 decades, that's 20 years. And they did run it in the two modes, one looking only for electron neutrinos, and one that shows all three types. So they have 2 different detection modes for their operation. And so they found that with the same experiment, if they are just detecting electron neutrinos, they mirror Bacall's result, Bacall and Davis's result, and they mirror the Kamiokande results, which is 1/3 missing. But with the same experiment turned on with all 3 detection types on, then they found the expected amount that Bacall predicted. So that solved it. And when they took into account the MSW effect, they were able to actually find it, which is really fascinating. Again, the Sudbury Neutrino Observatory was buried deep underground, a huge tank with photomultiplier tubes looking for the Cherenkov light. In any event, that solved an enormous riddle and showed conclusively that the neutrino observatories, by hunting for neutrinos, showing that neutrinos transform from one into the other, and it was an enormous undertaking from the 1960s to 2009 to actually discover whether or not fusion really did happen in the sun, and only in 2009, really, in 2006, was it proven that that fusion happens in the center of the sun. So fusion does happen in the sun. There is a way to detect the neutrinos. It's extraordinarily difficult. There's only a few neutrino observatories around the globe, but they have shown that they actually can detect the neutrinos. The neutrinos actually do work, can be discovered. You just have to be really, really careful and use an amazing amount of detection work. And what was fascinating is initially, the Hans Bethe's ideas about the proton-proton chain never included the concept of the neutrino oscillation, where they go from one flavor to the other. But that was discovered as a problem, and then the problem was then solved by looking at the nature of quantum mechanics and how these things can actually transform one to another. And then processes were shown that this quantum transformation between them actually does occur. So we now know that fusion really does occur in the center of the sun, and there are actual evidences of it coming out. And neutrino observatories are really important because they are direct measures of exactly what's happening in the center of the sun. So neutrinos are part of the equation, and they are important with respect to the discovery of what's happening in the center of the sun. Now, here's what's interesting. Neutrinos, the light that's coming out of the sun, and the neutrinos that are leaving the sun mean that, well, no party lasts forever because the hydrogen's being transformed to helium, whether through the proton-proton chain or the CNO cycle, and the helium itself can be transformed into carbon and oxygen. So eventually stars run out of fuel, and that assures that stars must change, that something must happen to the sun in the future when it runs out of fuel. So there's a lot of changes that have happened to the sun in the past and will happen to the sun in the future. So we'll be discussing that next time.